진심으로 감사드립니다. 저 또한 이 자리에 함께할 수 있어 영광입니다. 여러분께서는 지금 한국농어촌공사 KRC 아트홀에 와 계십니다. 오늘 행사는 온오프라인으로 동시 진행됩니다. 또 현재 유튜브와 줌을 통해 해외에 계신 인사분들께도 동시간 송출되고 있습니다. 따라서 한국어와 영어로 번갈아 진행된다는 점 참고 부탁드리겠습니다. 아울러 유튜브 채널 시청 시 영어 버전으로 시청하실 분들께서는 영어 버전 링크를, 우리말 버전으로 시청하실 분들께서는 국문 버전 링크를 이용해 주시기 바랍니다. 또 줌을 통해 회의에 참가하시는 경우 유튜브 채널을 동시에 시청해 주시기 바랍니다. Good morning everyone. Welcome to 2021 International Symposium of Smart Farming Strategies for Carbon Neutrality in the Livestock Sector. I'm the MC of today's symposium, Dae-Hee Park. First of all, I would like to appreciate all of you for joining us today. I'm so honored to be here with you. We are located at the KRC Outdoor of Korea Rural Community Corporation. Today's symposium will be streamed on YouTube and Zoom for people who are currently in a foreign country. Therefore, please notice that the show will be run both in Korean and English. Also, we provide English and Korean version of YouTube streaming, so please choose proper language link for your purpose. If you join through the Zoom, please watch YouTube streaming simultaneously. 오늘 진행되는 심포지엄은 전라남도 국제농업박람회와 농업기술원이 주최하고 순천대학교와 2세대 스마트팜 사업단이 추진합니다. 또 한국축산학회, 농림축산식품부 미래축산포럼, 한국반추미생물연구회, IKNC, 글로벌 하리스코, 농협사료 그리고 한국농어촌공사가 후원합니다. Today's symposium is hosted by the Jeollanam-do International Agriculture Exhibition and the Agricultural Technology Institute and organized by Suncheon University and the Second Generation Smart Farm Enterprise Organization. It is also sponsored by the Korean Society of Animal Science and Technology, the Ministry of Agriculture, Food and Rural Affairs Future Livestock Forum, Korean Society of Rumen Function Studies, IKNC, Global Harisco, 농협Feed and the Korea Rural Community Corporation. 먼저 본격적인 시작에 앞서 오늘 이 자리를 빛내기 위해서 참석해 주신 내빈 여러분을 소개해 드리겠습니다. 호명되신 내빈께서는 잠시 자리에서 일어나셔서 인사를 해주시면 감사하겠습니다. 참석자분들께서는 한 분 한 분 큰 박수로 환영해 주시죠. Today we have 10 honored guests. Please give them a warm hand. 자, 제일 먼저 사단법인 한국축산학회 회장이신 충남대학교 진동일 교수님 자리해 주셨습니다. Please welcome 동일진. 다음은 농림축산식품부 축산정책국 박범수 국장님을 소개해드리겠습니다. Please welcome 범수 Park. 감사합니다. 이어서 전라남도 농축산식품국 축산정책과 박도환 과장님께서도 함께해 주시겠습니다. Please welcome 도환 Park. 계속해서 소개해드리겠습니다. 전라남도 농업기술원 축산연구소 정지영 소장님께서도 자리해 주셨습니다. Please welcome Miss 지영정. 이어서 사단법인 대한한돈협회 전남도협의회 오재곤 회장님을 소개해드리겠습니다. 이어서 충남대학교 서성원 교수님 자리해 주셨습니다. Please welcome 성원 sir. 다음은 중앙대학교 김준모 교수님 소개해드리겠습니다. Please welcome 준모 김. 네. 이어서 순천대학교 양철주 교수님 자리해 주셨습니다. Please welcome 철주 양. 네, 이어서 경상국립스마트팜 연구센터장 김현태 교수님 와주셨습니다. 마지막으로 순천대학교 이상석 교수님 함께해 주셨습니다. 네, 다시 한번 오늘 자리해 주신 내빈 여러분께 진심으로 감사의 말씀 전합니다. 이외에도 정말 소중한 많은 분들께서 자리해 주셨는데요. 한 분 한 분 소개해드리지 못하는 점 양해 부탁드립니다. 이어서 진행 순서를 안내해 드리겠습니다. 본 행사는 크게 1부와 2부로 나뉘어 진행됩니다. 일부는 환영 인사 및 축사를 시작으로 기조 연설과 첫 번째 세션인 축산 분야 스마트팜 추진 방향 연설이 있겠습니다. 이후 12시부터 1시까지는 중식 및 휴식 시간을 가지도록 하겠습니다. 그리고 1시부터 진행되는 2부에서는 두 번째 세션인 탄소 중립을 위한 유럽 축산 분야 스마트팜 주요 기술 현황과 세 번째 세션인 전문가 패널 토의가 있겠습니다. 그리고 폐회사를 마지막으로 행사를 모두 마치겠습니다. This symposium will be divided mainly into two parts. First part will start with welcome and congratulatory speech of the symposium. And then there will be a keynote speech and the first session, direction of promoting smart farm in live sector. Then from 12 o'clock, there will be a break for an hour. The second part will start at 1 o'clock. There will be the second session, current status of major smart farm technologies in the European livestock sector. And the third session, overall discussion. Finally, the last stage, closing remarks. 그럼 첫 번째 순서로 이 자리를 축하해 주시기 위해서 마련된 전라남도 김영록 도지사님의 환영사가 있겠는데요. 이 환영사를 전라남도 농축산식품국 축산정책과 박도환 과장님께서 대신 읽어주시겠습니다. Now there will be a welcome speech from 전라남도 Governor Yeongrok Kim, and this welcome speech will read by Director 도환 Park of Livestock Policy Division. 그럼 박도환 과장님을 단상 위로 모시겠습니다. 뜨거운 박수로 맞이해 주시죠.
축산학회 회원 여러분, 축산인 여러분,
Members of the Korean
안녕하십니까?
Society of Animal Science and Technology and the livestock farming industry, good morning. I'm Governor Kim Young-nok of Jeollanam-do Province. I'm very delighted that the International Smart Livestock Farming Symposium is being held here in Jeonnam Province, the land of life. As we are all still struggling from the COVID-19 pandemic, today's international symposium will focus on smart farming strategies for carbon neutrality in the livestock sector with presentations and panel discussions on the path forward to bring our livestock sector to the next level. We will have presentations on advanced countries' cases and also a panel discussion. Our domestic livestock sector is swiftly responding to the changing consumer preferences for food products due to the pandemic, and this is only possible thanks to the solid foundation laid by members of the livestock community here with us today. Nevertheless, the negative perception that livestock industry is a key contributor to carbon emissions and diseases such as the African swine flu continues to threaten our livestock industry, and it is high time we draw up effective countermeasures. I believe some of the problems can be overcome by advanced stock breeding facilities and breeding systems. Furthermore, if the high-tech fourth industrial revolution technologies are applied to the labor-intensive livestock industry, farms will become more productive and provide a more pleasant environment to solve not only disease issues, but also enhance animal welfare. I hope today's International Smart Livestock Farming Symposium will help us recognize the current problems in the industry, learn from research conducted in advanced countries so that we could derive wise insights that can shape the path forward for Jeollanam-do Province and the domestic livestock industry. Finally, I express my deep gratitude to all members who spared no effort for a successful opening of today's International Smart Symposium, and to all supporters who made this event possible. October 28, 2021, 전라남도 Governor Kim Young-nok.
네, 지금까지 박도환 과장님께서 전라남도 김영록 도지사님의 환영사를 대독해 주셨습니다. 수고해 주신 과장님께 감사의 말씀 전합니다. 또 이 자리에 함께 하시진 못했지만 좋은 말씀으로 환영사를 준비해 주신 김영록 도지사님께도 다시 한번 감사합니다. There was a welcome speech by Governor Yeongrok Kim, and thanks to Director Do-hwan Park for proxy reading. 다음은 한국축산학회 회장이시자 충남대학교 동물자원과학과 진동일 교수님의 축사가 있겠습니다. Next is a congratulatory speech by Professor Dong-il Sin of the Department of Animal Resources at Chungnam National University. 진동일 교수님 박수로 맞이해 주시죠.
Good morning. I am Professor Jin Dong-il, the president of the Korean Society of Animal Science and Technology. It's early in the morning, and I drove all the way here from Daejeon, and the air is fresh here. The weather was nice and all the roads were very clean. And I was very impressed by the infrastructure in this Jeollanam-do province. It's a very pleasant environment with well-established infrastructure. That was my impression this morning. So I'm very delighted that the International Agriculture Exhibition is opening today's International Symposium on Livestock Farming and Carbon Neutrality. I express my gratitude to Governor Kim Young-nok of Jeollanam-do Province and the Director Park Bum-soo from the Livestock Policy Division of the Ministry of Agriculture, Food and Rural Affairs, who will deliver his keynote speech. Also, I want to thank all panelists who will present today from home and abroad and the second generation Smart Farm project team of Suncheon National University who organized today's event. As a new paradigm of carbon neutrality is shaping the world's future path, Korea's livestock sector is no exception to such global trends towards carbon neutrality. Although the domestic livestock industry continued to develop, it is still partly viewed in a negative light due to its contribution to pollution. When the media covers topics on carbon neutrality or greenhouse gas emissions from the agricultural sector, livestock is always pointed out as a major contributor. In such times, Korea's livestock sector should proactively pursue carbon neutrality in order to renew its reputation and promote the domestic livestock industry. Compared to other Asian countries or agricultural sectors, the Korean livestock industry is based on a well-established system which enables efficient response to changing trends. Our livestock industry weathered through what we perceived as crises, such as the Uruguay Round Agreement and the FTA negotiations, and still continues to grow. From this, I'm confident that we will successfully overcome current difficulties to bring our livestock industry to another level. To this end, today's International Symposium will allow us to look into and gain insights from advanced countries based on which we should build our own tailor-made carbon neutrality system to act upon. With regards to carbon neutrality, individual research and actions will not be sufficient, but consortiums comprised of field experts should gather relevant data and lead scientific efforts to cut back on carbon emissions. Furthermore, state-of-the-art Fourth Industrial Revolution technologies will actively be incorporated into stock breeding facilities, feed, and manure management systems to create a more pleasant environment, enhance farms' productivity, resolve disease problems, and solve animal welfare issues in general. This is my vision. Furthermore, consumers will come to see our cattle products as the safest and most high-quality food products, leading to an ideal, sustainable livestock food supply system that connects the producers, consumers, and industries. With today's International Symposium on the new carbon neutrality paradigm and the livestock industry, I hope we will together be able to dream about the bright future of the domestic livestock industry and take stock of the current status. I hope many fruitful discussions will take place in today's symposium and that we will be able to clearly establish a path forward towards carbon neutrality. Thank you.
네, 충남대학교 진동일 교수님께서 축사해 주셨습니다. 다시 한번 좋은 말씀 감사합니다. Thank you for your congratulatory speech, Professor Dong-Hee-jin. 이번에는 농림축산식품부 축산정책국 박범수 국장님께서 기조연설해 주시겠습니다. This time there will be a keynote speech by Director Bum-soo Park of Livestock Policy Division in Ministry of Agriculture, Food and Rural Affairs. 박범수 국장님을 단성의로 모시겠습니다. 뜨거운 박수 부탁드립니다.
예, 반갑습니다.
Good
저는
morning, everyone. I am
농림축산식품부
Director Park Bum-soo
축산정책국장
from the Livestock
박범수입니다.
Policy Division of the
오늘
Ministry of
기조연설을
Agriculture,
맡게
Food
돼서
and Rural
대단히
Affairs.
기쁘게
It
생각을
is a
하고요.
great pleasure to deliver
이런
this
자리들이
keynote
좀
speech
많아서
before
서로
such
이렇게 우리 축산
distinguished
문제에 대해서
guests.
이야기할 수
And
있는
I
기회,
think it's very
이런
meaningful
것들이
that we are all
좀
gathered
자주
here
있었으면
together to
좋겠다,
talk
이런
about
생각을
important
해봅니다.
issues in the livestock industry.
오늘 맨 첫 번째 화면 좀 예. 오늘 제가
The
말씀드리려고 하는
topic I've
거는
chosen
축산
for today
환경의
is change of the
변화
livestock
그리고 이제
environment
ICT
and
이
ICT
부분에 대한
technologies.
것입니다. 그러니까 축산업이 어쨌든 산업의
The
하나이고
livestock
우리
industry is
경제에서
one of the
차지하고 있는
important
비중이
industries
상당한데
of our economy.
축산업을 둘러싸고 있는 여러
And
가지 환경들
with
이런
regards
것들이
to
변하고 있다.
livestock industry, environment
이런
is
변하고
changing a
있는
lot.
환경에서
And
ICT가
within
어떤
this
역할을 할
changing
수 있을
environment,
것인가
what kind of roles can
그런 측면에서
ICT
한번
technologies
얘기를
play
해보고자 합니다.
is the topic that I want to cover today.
먼저 축산업에
First,
대한 이해
Let
뭐부터
us first
시작을
dive
하겠습니다.
into what livestock industry
아시는
is.
것처럼 축산업은
As you may all
우리
know,
가축을 기르는
livestock
그런
industry is an
산업이고 가축을
industry
기르는
that
과정에서
breeds stocks
축산 농가가
and
생산 요소들
produces livestock
노동,
products by
또
putting
자본,
in and technologically
이런
combining
것들을 투입을
production
하고
factors
그걸
such as
기술적으로
land,
결합을 해서
labor,
축산물을
capital,
생산해내는 그런
and other
산업이라고
production
할 수가
factors.
있겠습니다. 그래서 최종 생산물은
So what is the final
축산물입니다.
product of the
고기,
livestock industry?
우유,
It is livestock products including
이런
meat,
것들을
egg,
생산해내는
milk,
것이죠.
and honey.
이런 것들은 시장에서
These
팔
livestock
것이고
products
돈을 받고
will be
또
sold
소비자들은
in
그것을
the market
돈을
and
내고
consumers
사갑니다.
will pay
그래서
to
경제적
buy those
economic
products.
goods라고 볼 수
So
있겠습니다.
they are economic
시장에서 거래가
goods.
되는 것이죠.
So they are products that are traded
그런데
within the
축산업을 하는
market.
과정에서 이것만
But
나오는 것은
within the
아닙니다.
livestock industry, there
추가로
are
나오는
also
게
other factors, which
전-
is
페이지 좀 저기인가요? 그 앞 페이지요? 네, 여기. 아, 예. 이게 예. 잘 이게 작동이 안 되네요.
I don't
이
think
페이지
this is working
아까 첫
well.
번째 페이지.
But let's
예,
go
여기
back to
보여주십시오.
page number 1.
그래서 최종적으로
So
산출물 나오는
once again
거는
about final
축산물인데
product. The final
이것을
product
생산하는
of the
과정에서
livestock
의도치
industry is
않게
livestock products,
중요나
but
악취가 같이
unintentionally
나온다.
there are also other products
이거는
which are manure
negative
and stench, and
externality라고
we can
이야기를
refer to
합니다.
this as
이
negative
의미는
externality.
시장에서 아무도 분뇨나 악취에 대해서는
In the market,
비용을 지불하지 않는다.
nobody pays
이런
cost
얘기입니다.
for
그래서
manure
negative
and stench.
externality라고
So that's why we call this
시장
negative
가격의
externality.
분뇨나 악취 이런 것들이
Manure
여기에 대해서
and
생산자도
stench
지불을 하지 않고
is not reflected
소비자도
in
지불을
the
하지 않는다.
market
특히
price,
정부의
and
개입이
consumers,
없다면
producers, and
그렇게 이야기를 할 수가
when there
있습니다.
are no government
오른쪽에 그림을
policies,
보시면
nobody pays the cost.
빨간 선
So let us look at the
그게
graph on
정부의
the
개입이
right hand
없을
side.
때의 시장
The
분위기.
red market supply
검정선이
is market
시장의
supply
수요가 되죠.
without government
그렇게
intervention,
되면 시장에
and the
가만히
black
맡겨놨을 때는
line is
그
market
빨간 선
demand.
밑에 있는 수준에서 생산이
Then
될 겁니다.
the intersection between the market supply and
그런데
market demand will
말씀드린
be the
대로
price
분뇨나
of
악취가 나오게 되면
livestock
이것은
products. However,
사회적
if there
비용이기
are
때문에
manure
그
and
비용을
stench,
고려했을 때
then this
사회적 공급
is
곡선은
going to
파란
lead
선이 될
to
겁니다.
social cost, and this is going
그러면
to be reflected in the blue
사회적으로
line, which is
바람직한
supply
수준의
considering
생산,
social cost.
socially preferred
So
production
socially preferred
이거는 파란
production
선 밑에
level
있는 수준.
will be
거기가
the
되겠죠.
blue line and
그래서
below.
시장에 가만히 맡겨놨을 때는 빨간
So
선의
if we
생산이
just
되고
leave it to the
사회적으로
market,
바람직한 수준의 생산은
the
파란
market supply
선이니까
will be red,
그
and
차이만큼이
supply considering
시장의
social
실패,
cost
마켓
is
페일리어다
blue,
이렇게
and the
이야기합니다.
gap between the two is market
그래서
failure.
우리나라뿐만 아니라 모든 나라가 이
Not only
사회적
Korea,
바람직한
but
수준의
also
생산 이 부분으로
other
유도하기 위해서
countries
여러 가지
are
regulation을 합니다.
introducing many regulations to reduce this market failure. For example, there are regulations and restrictions related to density, emissions, and also
pollution tax. Pollution tax is a tax that is levied on pollution. Then the market supply will equal supply considering social cost. And this is going to lead to optimal market supply, and market failure will disappear. So in the process of running the livestock industry, livestock products are produced and they are once again sold in the market. So the livestock industry is inevitably affected by market environment, social and economic changes. Because this is an economic goods, it is exposed to market environment. So when the supply changes, then the price changes. And regarding social and economic changes, what I mean by that is this blue line, supply considering social cost, this will change according to social and economic changes. It could be near the market supply line or it could be far up there. So the livestock industry is vulnerable to all these external factors. So how is the livestock environment changing? I think this is a very important topic we need to discuss. This is because there are many environmental factors that affect the livestock industry. And today I would like to mention two major trends. First is post-COVID era and with COVID era. I think that these two mean the same. From November, I think that we will be moving towards with Corona era, and after the COVID-19 era, I think that there will be a lot of changes. Of course, we have already experienced a lot of changes, and going forward, we will also face diverse changes. And what is going to happen after the COVID-19 era? In order to answer that question, we need to take into account two characteristics of COVID-19, and we also need to learn from the experiences of past pandemics, and we should compare and contrast COVID-19 with past pandemics. So first characteristic is fast and worldwide. This means that the disease, COVID-19, it spread rapidly across the globe. This might be a unique characteristic of COVID-19, but what we need to take into account is globalization. After Uruguay round and the establishment of the WTO, and with globalization, international mobility increased significantly. So virus travels along with people and along through the logistics system. So this is what I mean by fast and worldwide. And with the spread of COVID-19, mobility is restricted. Recently, many countries are considering introduction of vaccine pass, and without vaccine pass, domestic and international travel will be difficult. And we also talk a lot about great logistics disturbance and labor shortage, including foreign workers. So these are all examples of reducing mobility, which are leading to some problems. These are accentuating the importance of food security. Particularly advanced countries, not only agricultural foods, but also other foods need to be maintained at a certain level of domestic production, and they are storing a lot. And some of the countries are even stopping their export of their food production. So this is characteristic A. And characteristic B is strict social distancing. Now, we have been disconnected with each other, but we are virtually connected. We are connecting and interacting with each other in the online world. So, interaction between people is changing from contact-based to contact-less. And we believe that this regime will continue going forward. So we expect there will be an increase of contactless production, distribution, and consumption. So these will be the characteristics of the post-COVID era. And second major trend of the changes in the livestock environment is carbon neutrality or net zero. As you may all know, carbon neutrality is the topic for today. We believe that we are going to enter the era of carbon neutrality, and for the Korean government, they announced 2050 carbon neutrality. Carbon neutrality related efforts kicked into high gear since the inauguration of Biden administration. COP26 is upcoming and methane pledge will be signed soon. Demands for carbon neutrality is increasing significantly, and social threshold of the livestock industry's negative externality increased. In the past, when there were manure productions, people didn't care a lot, but now it has become a significant problem that needs to be resolved. But what's the future direction of the livestock industry given the fact that we cannot forcefully downsize the industry? This is a very important question we need to consider. So according to the two characteristics that I've mentioned, let us think about what kind of changes will take place in the livestock industry. First, in the post-COVID-19 era, food security will become more important, and there will be increase of contactless production, distribution, and consumption. We need to maintain a certain level of domestic production, but there are also restrictions on building new stables, particularly because of space. We need to secure space to build new stables, but we don't have enough space. And under these restrictions, we need to still maintain a certain level of domestic production, and that's where ICT technologies come in. The answer lies in increasing productivity by adopting ICT technologies and database precision feeding and others. This could be a very significant clue. Second is the increase of contactless production, distribution, and consumption. We are now suffering labor shortage because we are short on labor workers and labor cost is increasing. And the answer lies in automation through cutting-edge equipment powered by ICT technologies. And when we introduce cutting-edge technologies, of course, the cost could increase initially. However, in the longer term, this can cancel out the labor cost increase. So ICT technologies and adopting those technologies will definitely lead to decrease of labor cost and production cost. And in the age of contactless production, distribution, and consumption patterns also change. You might have delivered a lot of delivery foods when you stayed at home because of COVID, and there are increasing demands for HMR, home meal replacements. Now there are increasing demands for processed products, and we need to focus on these. And small packaging is also on the rise, and meat cut-centered distribution is the future that we need to be headed in. And let me talk about carbon neutrality and increased use of ICT technologies in the livestock sector. We need to reduce animal waste while maintaining appropriate domestic production, and finding the method to do so is important. And secondly, we need to come up with appropriate treatments of manure. Production should be decreased, and if produced and emitted, they need to be treated appropriately in order to move towards carbon neutrality. So reducing the amount of manure is simple. The method could be reducing the population of animals. However, this runs contrast to food security. So that's why ICT technologies should be adopted in the livestock industry. If we can feed less and keep productivity, then this is going to lead to reduction of methane and greenhouse gas emissions. And ICT technologies can enable these. Precision, management, and specification are the technologies that we can adopt. And second is environment-related technologies. Even with less feed, greenhouse gas emissions could decrease. So we need production methods with less greenhouse gas emissions, even with the same amount of feed. And some examples are low methane, low protein feed, and improvement of cattle breeding methods. And second is appropriate treatment of manure. In the case of Korea, individual farms, they treat the manure and then they distribute that in their farms. But I think that public treatment of manure should be expanded. And we also need to capture manure in order to reduce carbon emissions. So in the case of cattle feed, we need to make them into solid fuel, and another idea could be making biochar. Recently, in Tangjin Association, they introduced biochar and they decided to adopt it into Hyundai Steel. And a lot of energy companies are using cattle manure to change them into solid fuel. So there are a lot of companies and businesses that are saying that they're going to use cattle manure as an energy. And in the case of swine, we can make them into energy too and make electricity and share that with local communities. And if that's impossible, purification and discharge should play a role. So there are many methods we can use to purify and discharge manure. As such, ICT technologies could be used in various methods. So this graph might seem complex, but I will provide you with a simple explanation. This is already what I have explained. At the bottom, there are two lines, and there are also two curved lines. The y-axis is the benefit that we enjoy from livestock products or benefits that we enjoy from the environment. And the x-axis denotes input and emissions, production, and consumption. So when we produce livestock products, by feeding them, we enjoy a lot of benefits from consumption. Then the graph goes up towards the right. However, and the satisfaction level increases significantly. However, it plateaus out if it exceeds a certain level. So we have this curved line on the top. And what is the benefit from the environment? If we don't breed livestock, we can enjoy the environment to the fullest, which means that the satisfaction level will be 100%. However, if there is manure and stench, then the benefit will decrease. If we produce a little, the velocity is not really fast. However, if there are a lot of byproducts produced, such as manure and stench, then the curve goes down rapidly. So the two lines at the bottom, the blue lines at the bottom, are the benefits from environment, and what goes up is benefits from consumption. So what about total benefit? Total benefit is the combination of these two lines, BC and BE, and that will be the blue line on the top. So what is the optimal level of input, production, and consumption? That will be point Z. That's the optimal point. However, what is the reality? Where do we stand? We stand on the right side of the optimal point Z. We now stand at N. So why is this? As I've already mentioned in the first page, this is because of surplus supply and also negative externality. Moreover, if we take into account social regulation, there are a lot of farmers that actually don't comply to government restrictions and regulations. But what is the socially optimal point? It will be Z. So carbon neutrality is pushing us to reduce our production. So we have to reduce our production from N to Z. And this is a major shock to the livestock industry. If we reduce the production this much, it's going to be a major shock. So what do we have to do? This means that we have to lift up the graphs at the bottom to the top. So the benefit increases with consumption and with adoption of ICT technologies and with precision farming. With the same amount of input, the production should be the same. So less input and increase of production, and that's how we can shift the line to the red line on the top. And if we have low methane feed, then even with the same amount of input, methane emissions will be reduced and greenhouse gas emissions will be also reduced, which means that the line will go up also. So the line will shift to the red line. So the optimal line is the red line, and that's our goal. And we think that if we adopt optimal and state-of-the-art technologies, we would be able to achieve this red line. And the lines of optimal and actual will overlap and match. And that's where carbon neutrality could be realized. And this can be empowered by ICT technologies. So we need to change this N from N star with compliance of regulation. And with technological development, we need to lift up the line from the bottom to the top and change from Z to Z star and from N star to Z. And once again, ICT technologies will enable this. So this is the key message for my presentation. To respond to the changing livestock environment of the post-COVID era and for an appropriate manure treatment and sustainable development of the livestock sector in the age of net zero emissions, it's time for us to fully embrace ICT technologies and fully develop ICT technologies. And I believe that this is an important role of the government. Let us collaborate together between the academia and the government so that we can move forward to carbon neutrality. Thank you.
지금까지 박범수 국장님의 기조 연설이었습니다. 수고해주신 국장님께 감사의 말씀 드립니다. 다음 순서는 오늘 심포지엄의 첫 번째 세션인 축산 분야 스마트팜 추진 방향에 대해 충남대학교 서성원 교수님께서 좌장을 맡아 진행해 주시겠습니다. Next, Professor Sungwon Seo of Chungnam University will be the chairperson of the first session. 이번 세션은 총 2가지 주제로 진행됩니다. 먼저 첫 번째 주제인 축산 분야 정밀 사양 관리를 위한 스마트팜 기술 전략을 경상국립대학교 스마트팜의 연구센터장 김현태 교수님께서 맡아주시겠습니다. 다음 두 번째 주제인 탄소 중립을 위한 미국의 축산 분야 스마트팜 발전 전략은 텍사스 A&M 대학교 어그리라이프 리서치의 루이소 테데스키 축산학 교수님께서 맡아주시겠습니다. This session will be held on two topics. The first topic, Smart Farm Technology Strategy for Precise Specification Management in Life Sector, will be proceeded by Professor Hyun-tae Kim, the Director of Smart Farm Research Center, Gyeongsang National University. The second topic, Smart Livestock Farming Strategies for the United States, will be handled by Luiso Tedeschi, an animal science professor of AgriLife Research at Texas A&M University. 먼저 이번 세션의 좌장이신 서성원 교수님 모시겠습니다.
예, 반갑습니다. 일부
morning.
세션 좌장을 맡게
I
된
am
충남대학교
The
서성원입니다.
moderator
그리고
for
여기
the
지금
first session,
뭐
서성원
있는
from
거에서
Chungnam
나옵니다만
National
차세대,
University.
2세대 추구 스마트팜
And
그
the second
사업단
generation
그
Smart
연구
Farm
책임자를 맡고
project
있습니다.
team is where I am
사회자께서
the team lead.
한글하고 영어로 이렇게 번갈아가서 말씀하셔가지고
So
제가
the
굉장히 긴장을 하고 있었습니다. 이
MC
한글하고
spoke
영어를
both in
번갈아가면서 해야
Korean
되는가를
and
제가
English,
긴장을
so
하고
I
있는데
was nervous. I
소개를
thought
이미 다
I had
해드렸기
to
때문에
do
영어로
so,
그냥
but
한글로 하도록
since all the
하겠습니다.
introduction was already
저희
given
그
in English, now I will
스마트라고
just proceed
하면
in
저희가 이제
Korean.
스스로 모니터링,
So self-monitoring
분석하고
and
리포팅,
analysis
보고하는
and
그런 기술을
reporting
얘기합니다.
are
가봉수
the
부장님께서도 아주
technologies
좋은
used
말씀 많이
in
해주셨는데 역시
smart farm and the
경제-
livestock
경제학
sector.
박사셔가지고
Well, the keynote
뭐
speaker
과학적으로 분석을 잘 해주셨는데
was an economist, so
제가
he
그런
gave a
얘기를
very
하면 스마트팜이라는 것이
scientific
결국 세대는
analysis,
세계는
but
올 수밖에 없다.
in fact,
우리가
smart
실험도
farm is a trend that we will
스마트폰을
not
쓰듯이
be
어떻게든
able
스마트팜의
to avoid.
세대는 올 수밖에
The
없다라는
generation
얘기를 하면서
of smart
그래서 지금
farm
일부에서 어떻게
is an
보면 약간
inevitable
후발대라고도
future.
할 수 있지만
So
금방 선진국이 될
while we
그
are
한국과
slightly a
미국의
latecomer, we will soon
그
catch
아주
up
훌륭한 연구사
with the advanced countries in the smart farm sector. And I'm excited to hear presentations from the experts in this session. So our first speaker is Professor Kim Hyun-tae, who is the Dean of the Smart Farm Department of the Gyeongsang National University. Professor Kim Hyun-tae will be giving his first presentation for this session.
오늘도 재밌는 게 그겁니다. 김현태 교수님께서는
There's something interesting to note. In fact, Professor Kim will focus on the engineering technology in agriculture, while the second speaker, Professor Tedeschi, will focus more on the livestock sector. So we will hear both about the agriculture machinery and also the livestock sector technologies. Well, Professor Kim has two PhD degrees. He did one in biotechnology and another one in environmental science. So now let's welcome Professor Kim Hyun-tae with a round of applause.
예, 알겠습니다.
Okay, thank you.
반갑습니다. 경상대학교
Good morning. I am Kim Hyun-tae, Professor Kim Hyun-tae from Gyeongsang National University. I didn't know that this symposium was such a big event. I just thought it was a very simple request for a presentation and just came lighthearted, but now seeing such a big audience in front of me, I feel I should brush up my presentation.
하여튼 근데 오늘 제가 사실은 제일 첫 번째를
Well,
그 저기
I
인물도 아닌 것 같은데
don't-
이성석 교수님한테
I'm not sure if I'm
사실은 너무
appropriate to
기괴하게
give the first
제주도에
presentation
있어서
of such
지금
big
마치고 빨리 가야 된다고
symposium.
해가지고 제가
But
농협회 부회장을 하고 있어가지고
In fact,
그래서
I
그들이
am a
지금
vice president for
좀
another
앞으로
society
땡길 수 없나 그래서
where
제가
there is another
그 제일
event
첫
being
번째
held in Jeju Island today, so I have to
발표를
leave right
하겠습니다.
after this
그리고
presentation. So that's why I'm giving this
아마
first presentation.
둘이서 해야 되는데 마침 국장님께서 한
And
15분간을 더
actually, the
써주셨어요.
keynote speech was
사실은
longer, 15 minutes
고맙기도
longer
하고
than
또
expected. So
이렇든
I
저렇든 제가
guess
가지고 있는
I
어떤 여러 가지
have
경험들을
a
한번
shorter
얘기는
time allotted for my
해보겠습니다만은 혹시나
presentation. I'll try
그게
to
전체 주제와
do my best
관련해서 제
to
말씀이
convey
조금
my key
결례가 되지
message.
않을까 사실 조심스럽긴
And
합니다. 그럼에도
I
불구하고
am a
우리
bit
저기
cautious
순진대학교
whether all of my
양홍
messages
교수님
will be aligned
불러주셔서
with
감사합니다.
everyone's views, but
저는
still, I am
사실은
very
그 조금 전에
grateful to have
스마트팜
this opportunity to give this
학과라는
presentation.
학과를 만든 거는
In fact,
현재
the
양철
Department of
교수님 계시지만
Smart
2년 전에
Farm
DK를
was
양교수님하고 이렇게
established 2 years ago.
경쟁을 해가지고
We
저희들이 떨어졌습니다. 근데
actually lost the
이미 만든
competition for the
학과가
BK
존재를 하고
funding
학생들이
project, but
계속 지원을 해서
still
지금
we saw
학과를
many
맡고 있고
applicants
학부 소속은
coming into the
그
Smart Farm department.
농업기계공학과입니다.
And it is
그
under the bigger
농대를 보게
division
되면
of
생명을
agriculture
보게 되면
machinery.
전반적으로
If we look at
생물 베이스,
life
생물학
science,
베이스에서
it is
출발했습니다.
based
조금
on
이따 제가 다시
biology.
말씀을 드리겠습니다만은 공학
Well, I
베이스는
will
그렇게
elaborate
큰
in
비중을
detail
가지고 있지
later,
않습니다.
but engineering
그래서
is a
사실
small
지금까지는
portion of
어떤 측면에서는
that
저희들
huge
분야에서 사실은 많은 칭찬을
discipline,
받았다고 해도
and
과언이
it was
아닌데요.
largely
그런데
neglected
배가
in
물이 들어왔어요.
our
근데
academic
사실은
sector.
모절 사람이 많이
But
없어가지고 고기가 좀 잘 안 잡히는
actually, there
부분도 있습니다.
weren't that many
그래서
experts nurtured in
어쨌든
this
이런저런
field,
지금
and that's
제가
why
좀
it's
오늘
taking time to
말씀드리고
take
싶은
off.
부분은
But
대부분의 축산에 계시는
I
분들일
want to
거라고 생각합니다. 이런
emphasize
과정에서 저희들
that
공학자들하고
to all of the members of the
어떻게
livestock
서로
industry,
협조하고 협력하고 이렇게
that
해서
we
조금 전에
should
국장님 말씀하셨듯이
explore ways to
이런
collaborate
기술
between
개발이
the engineering sector and the livestock sector and see how those advanced technologies could open up new potential for our domestic industry.
제가 지금 제 말씀을 한번 드리겠습니다. 그래서
So,
저는 사실은 원래
moving on.
제목이 기술 전략 이렇게
In fact,
하거든요.
the original
근데
title
사실
for my
대학교에서
presentation
뭐
was
전략을 세우고
Technology
이렇게 하기에는
Strategy,
사실 굉장히 한계가
but
많습니다.
strategy is not the part where we professors are most prominent in. In fact, we focus more on the development of the technology itself. So I would like to elaborate more on what ICT technology is relevant to smart farming. Well, I don't feel I know enough to elaborate deeper into the big subject of carbon neutrality, so I will focus more on technology. Do you have any idea what this picture is implying here? Well, when I give special lectures, I always bring this picture, this diagram. Well, I feel like this is a more formal setting, so I'm not sure if I can just walk up to it and point out pictures, but I'll do so. Well, starting from end to end, we start with cannibals all the way to plants. But where do we get animal protein from in our diet? This picture shows exactly that point. Well, we have hot controversies about whether we should continue eating dog meat or not. Back in 1988, when Olympics were held in Korea, it was a hot topic, but it's once again becoming a very hot potato. Many people are opposing to the idea of eating dog meat. And after the 1988 Olympics, there were some attempts to separate dogs bred for meat and other dogs that are pets, but it's seen as rather savage from some people. And it's very difficult to really set or establish a consensus on such topics because it depends on the different cultures of the different countries and the traditional dietary habits. But, well, looking at it from an engineering or technology perspective, we will see a progress of trends. But what I think is it is difficult to eat an animal once we feel like that animal understands our language. There are many TV shows on animals, and there are shows that closes up on analyzing behavior and habits of dogs, and that highlights how humans and dogs communicate with one another. So we feel like they understand us. And then going further, what if pigs start protesting? Why don't you eat dogs, but why do you eat us?
이전에 식육 쪽에
Well,
근무하시는 분들이 많이 이제 배양육 쪽으로 미래의 어떤 그런
many
상황들을
people try to
준비하고
look
있는
into
걸로
the
저는 알고
future
있습니다.
to
그리고
prepare
인간의
on
단백질
how we
공급을
should
동물성 단백질 공급을
breed
동물에서 직접 얻을
animals.
수 없다면
Well, if it
우리가
becomes
결국
difficult
만들어야
to
됩니다.
get our animal protein intake from animals, then we are going to have to make food products with such proteins.
동식물의 언어 해석하는 과정에서
So the whole process of analyzing animals' language,
나오는 기술들이 산업화될 때 그게 사실은
once such technology becomes industrialized, then those technologies have to be incorporated into smart farm and livestock sector. So right now we are at this point, we are focusing on dogs. Well, let's move on to the next slide. This is a slide that I made when I was writing my thesis for my PhD, but I still use this for my special lectures, and I think I will continue to use this one until I retire. But the gist of this slide is very simple. This is me, actually, when I was much younger. If human can understand languages that animals use, we are focusing more on interpreting animal language. And how will we send signals to them? Well, we are doing much research on biochip, but we are looking at ways to make analysis in a non-intervening manner. So when we are trying to analyze animal activities such as excretion and feeding, we are trying to interpret their activities. And in the past, when we were measuring humidity and temperature, we were trying to figure out what was the optimal condition for breeding those animals. So in such technology research, we're looking into topics of PLF, smart farming, smart livestock farming. So now such technologies to interpret animal behavior is becoming more important, and we should look at where our technology stands right now. And I would like to share some results from the research that we conducted. Well, this will be the contents of my presentation today. First, I will question whether smart farm is the right terminology to use, and then I will show the study results and the trends both home and abroad. So, the term smart farm has evolved. Well, we did a lot of research at the Suncheon National University with sensors and looked into how to incorporate ICT into this sector from 15 to 20 years ago. And smart farm, smart factory, smart cars, smart city became the hot key word across many sectors. Well, it's important to use the terms in an accurate manner, but due to ongoing research in the field, we are seeing an evolution of terminology from smart farms, smart agriculture, digital agriculture, precision agriculture to vertical farms and other ICT, IoT relevant terms. I think the concepts have slight differences, but if we look at it from a high level, biotechnology played a big role in agriculture, but due to many reasons, engineering, ICT, and telecommunications are replacing the role that biotech used to play. So that is leading an evolution of terminology. If we look at the livestock industry, Well, there's still the question of what is the appropriate terminology among academics or policymakers in the livestock sector that will well reflect the incorporation of ICT technology in this field. Because many people, all citizens, usually think automatically about greenhouses when they hear the word smart farm. Oh, so I guess they're talking about protected farming or bare ground farming. But when they hear the word smart farm, they automatically think about the protected farming in greenhouses. So, well, if we say smart farming in livestock sector, I'm not sure if that will effectively convey the nature of the concept that we are talking about. So we need a refining of terminology.
And what is more interesting is, let's take a look at this slide. So this is a very simple statistics, but it has an important message that we can ponder upon. In 1970, I was in elementary school, and in 1970, the farm population was 45.9%, so it's near 50%. At the time, so just to simply explain, one farmer could provide one city dweller with a food, and that makes the food supply 100% one-on-one. This is just making everything simple, but that was true. However, in 2019, this figure dropped to 4.3%. If we reach 4.3%, this means that one farmer needs to support 20 to 25 city dwellers. So why did this figure decrease so significantly? This is thanks to machinery of farms, farm machinery. But this is not the end of the story. Let us make an expectation. So how do we expect that farm population will reduce? But the academia is trying to explain this. Researchers from Japan say that their number dropped to about 2%. And if this figure drops to 2%, this means that one farmer needs to support 50 city dwellers. So it is double the number that we have to support now. And if we look at the overall time frame, everything is changing. But with farm machinery itself, we cannot support such a big number of people. This is because there are limitations related to technology and also the size of the field. Tractors can be renewed, but the demand itself doesn't increase. So why and how will the number decrease? And the answer lies in ICT technologies and what we often refer to as smart farm technologies. If we don't adopt these technologies, we have no answer on how we are going to support so many people with so little farmers. So this is an important question we need to ponder upon. Let us think about this question together. I think that this is an irrevocable trend.
하여튼 그래서 지금 오늘 주제 중에 하나 과연 이제
So one of the
스마트
topics
팜,
that I
스마트
wanted
축산.
to
통상
discuss
우리는 이제
today
공업 쪽에
was
얘기를 하는데
smart
오히려 농업
industrial
쪽에 얘기를.
enterprise
우리 저기
and
서교수님이 아침에
farming
처음에
and farmers.
저한테 소개했던 것 중에 농공학과 출신. 예, 맞습니다.
So I
농공학과.
was introduced that I am
농공학과.
agro-industry major,
70년대, 80년대
which is the
농대가
combination of smart
만들어지면서
enterprises
그때
and
농대
farm
안에
and
있는
farmers.
농공학과라는 게 있었습니다. 그게 농공학과 출신. 제가 이게
So I
농공학과라는
majored in agro-industry, which is the combination of the two.
두 개의 기술이 조금 전에
Smart
제가
farm
이제
technologies,
OECD나 이런 데서도 계속 얘기하고 있는 것
as
중에 하나가
I've already mentioned, OECD and many international organizations are focusing on climate change, which is a visible problem. How much methane emissions is the livestock industry recording, and how much carbon emissions we can decrease from the energy industry are the problems that international organizations are focusing on. However, overall, in the agricultural industry, we need to think about agriculture, food, climate change, and future industry such as platform businesses. So this is the last technology of our generation, and the language interpretation of plant is the problem of our next generation. And if there are people who are now studying and researching upon these topics, I think that this is a topic worth researching. There are many definitions of smart farming, and one of the common definitions is indoor and outdoor farming, leveraging automation and smartification. However, we shouldn't be fixated on this definition because farming and agriculture is a very general and it's a very wide discipline. But if we try to limit the boundary, we are going to face a lot of challenges. So smart farming, precision farming, smart agriculture. Just think about the broad concept. Don't try to limit the definition of all these terminologies. Many people have different perceptions regarding smart farm, smart agriculture, and smart livestock. As I've already mentioned, some people think about greenhouses and some people think about sensors, and they can be all referred to as smart farming. As of now, I don't think that providing these definitions is the key issue that we need to resolve. Now, we need to think about the general concept of smart farming and smart agriculture. That's the right approach. And this is the repetition of what I've already said. Our engineers, they are trying to answer this question. So smart farming is about hog breeding and increasing convenience and increasing productivity. But how about price? How about price? This is the question, which is very important from an industrial perspective. For researchers, it might be an insignificant question, but from an industrial perspective, productivity, convenience, and at the end, price is important. Price is an important factor that we need to consider, and particularly for farmers, price is very important. In protected horticulture, there are a lot of sensors, and smart agriculture also need to adopt the technologies of protected horticulture. So we are piloting these ideas, and a lot of infrastructure is now being set up. But still, traditional farmers, they are thankful about government subsidy, but as a matter of fact, when new machines and equipment they come in, they don't use them practically. So these technologies need to be connected to machineries, and this needs to be connected to consumption too. This is very important.
이거는 여러분들 너무 많이 봤기 때문에 간단하게
I know that you are very familiar with this, and I would like to mention about the fourth industrial revolution, and the most important part is this orange box.
50%더 만들어내요.
We need to make 50% more labor, and we need to make 50% more labor in this orange box.
그러니까 인터넷 인공지능 하여튼
AI is the key technology that we need to leverage.
이것도 그냥 넘어갑시다. 너무
So
많은
let's
얘기를
just
들었어요.
skip.
그래서 지금 보면 전반적으로 저희들이 이제 공학자들 입장에서 사실 저희들 연구실도
So,
축산뿐만
us
아니고
engineers,
필드에 대한
not
자동화기술
only
개척들,
livestock
온실의
sector, but all
작물
other
생장하고
sectors
개들
are sort of a focus of our study. We
연구를
look at
진행하고
crop
있는데
farming
사실은 이런
and other
전반적인
agricultural
한
sectors.
6개
And
카테고리에서
if we
우리가
look at the
스마트
overall
파밍을
6
쓰고 있는
categories,
것
we
같습니다.
are applying the term smart farming.
특히 이제 축산 쪽에서는
And in the
축산 쪽에서는
livestock industry,
그러니까 지금 한 번쯤 또 이게 그 데이터 이렇게 막 얘기를
data is the key word. Of course, data is an important factor and we need it.
뭔가가 이렇게 정리가 안 돼 있는
However, I think that nothing is well organized as of now. The government is investing a lot in this sector. The government has enough budget, but what are we going to do with accumulated data is something that we need to work upon. There is room for improvement.
조금 이따 다시 말씀을 드리겠습니다만은
I will mention this later too, but in the livestock industry, the key question is, for what are we going to accumulate data? This is a key question. Up until now, for livestock environment and for temperature and humidity and temperature-based sensors were the key factors, and we thought that developing these will lead to carbon emissions abatement. However, in the next step,
동물들이 어떤 뭐 그게 돼지가 됐든 소가 됐든 또
whether it be pig, chicken, or cow,
걔들의 정보를 이렇게 쭉 받자는 거예요.
we need to accumulate data related to these animals. However, what for? Why are we accumulating data is the question. We need to have a target. We need to have a clear objective. So if there are policymakers within this room, I suggest you to ponder upon this question. To decide upon the utilization rate, we need to think about whether the data accumulation will be per minute, per hour, or whether we are going to average out these figures. Should be set. And this leads to another topic of standardization. But the key question is what? For what are we going to accumulate data? So in our research center, we made a crowd-based system, and in our R&D center, we have 6 greenhouses and 2 plant factories, and we are accumulating data of these. CO2, temperature, humidity data is being monitored, and those that cannot be directly monitored are being manually monitored. So this is real-time data monitoring system result. We're doing this in our research center. So the data that we extract from the research are independent variables, and dependent variables need to be connected with independent variables, and we need to relate this to artificial intelligence technologies. These are all statistics from our research center.
이게 또 라이브 그 저기 그 뭔가 갑시다.
Okay, let's
그래서
skip.
자 그러면 이제 조금 더 우리가
Then now,
현실적으로 어떤 인구들이 지금 우리 가까이에 있는지 실제로
what
어떤
kind
것들이
of
이용되고 이제
technologies are being adopted in farming and the livestock industry? We are always talking about smart farm industry and robotics and automation. And if all of these are realized, I personally think that robotics technologies are one of the most developed ones. Robots that cultivate is a hot topic in protected horticulture, but there aren't many products that are commercialized. So it's a very advanced technology, but nevertheless, the livestock industry, they don't have sub-machines and technologies that can support the main technology. Protected horticulture has the capability to accommodate more technologies. And from a few years ago, the Netherlands have introduced a technology named Lely, which is a milking robot, and the Netherlands Free Bar introduced a greenhouse environment control system.
모르겠어요. 이게 우리가 무엇이 조금 부족한지는 잘 모르겠습니다만.
Well, not exactly sure exactly what are the shortcomings that Korea has compared to other countries, but it's a fact that Korea is slightly lagging behind. That is why we are importing all these technologies. So, as we were pondering upon what area needed more research, I would like to introduce some of the research results that we've been conducting. This is a data construction project that is funded by the government. Here, we can also see that we must first define what we are supposed to provide to whom. Are we going to provide data to scientists or the farms or the policymakers? That is what should be figured out first. Since that is not clear, we are just simply gathering and collecting data currently. Well, I'm not sure if I can be so blunt about this issue, but actually the Information Institute, the promotion agency, is just simply collecting data. And, well, there is some connection with the New Deal programs, so they are putting much investment into this project. But collection of data on Korean cattle and swine, well, that is what the current project is focusing on. But there is some unclarity surrounding who the ultimate end user is. Who will this information serve? We have this incoming data, and they think if we leverage this data, that will lead them to somewhere, but it's not clear at this point. So, well, that was a brief introduction of this project. And in this case, this is a research that we are conducting in our lab. I briefly mentioned it earlier in my talk today, but this lab has been running for 5 years now. Well, the biotechnology based on biology and chemistry have many researchers from the academia or the research institutes or the government. They are mainly running research in this lab, and they've contributed greatly to much progress in this field. But as I mentioned, we are running out of human resource in this area. Machinery will not be able to fill in the gap for a lack of human labor. So we will inevitably have to turn to telecommunications network and ICT. Based on mathematical and physics, these technologies are applied, so we need experts in that field. We have math and biology and chemistry and physics as subjects that we learn in high school. So I think we need more talents who majored in math rather than just simply biology. But professors, they are rather reluctant to sort of integrate departments with other disciplines. But I'm sure we will have some visionaries who will be able to see the bigger picture and be more open-minded. But I think we need more interdisciplinary fields to develop the necessary technologies for the future. This is a slide that I used when I conducted research jointly with Professor Yang. This is another study that we are running at the lab. Before ICT, well, this is also partly ICT, but temperature, humidity data was mainly used to control the environment. But also, we are looking into biometric data and behavior analysis to make automated devices now. And we also need devices to collect biometrics data, so that is the focus of the current research. Well, in the near future, I think farms are rather reluctant to adopt such new technology because they are currently already using some technologies that they are familiar with, and they are worried that if they change devices, that would perhaps damage their yield or production. So when we are running such tests or pilot tests, then it should be fully funded because farms are not that voluntary. But we need to balance the use of software and hardware. Well, I may be repeating myself a little bit, but in fact, animals and livestock and plants, they are all affected by both internal and external factors, and they will give expressions in the form of behavior that shows how they react to those factors. There may be fever, and we should leverage many technologies that picks up those biometric signals. We could use video analysis or the separation of light technology or GPS and other such technologies. There's active research being conducted in that field. Nevertheless, in the livestock industry, I think technology is mostly centered on image processing. But I hope that we will be able to diversify the kinds of technologies incorporated in the livestock sector. This is an artificial intelligence technology, but I'm getting signs that I'm going over time, so I'll try to skip and spare you the details. Well, going into detail about the experiments happening at our lab, we are running analysis based on the neural networks, the behavior, the face, or other biometric signals of the pigs are being analyzed. Well, I'll briefly talk about a paper that was published in an academic journal. I'm sure you saw as you major way into this conference room, there is a heat sensing device.
왜냐하면은
but it
여러분들
may not be
그
that
이 중국의
accurate
손바닥이나 이런 데
because
체온이
the temperature on your
39도까지 잘
palm,
안 올라갑니다.
it rarely goes
굉장히
up to
많은 보정을
36 degrees
그래서
Celsius.
그러니까 우리 돼지들이
Well,
본사 안에서 여러 가지
here,
상태에서
if you look at the
온도를
pigs
측정하는
in
기술들입니다.
the feedlots, we try to measure their temperature and
AI 가지고 CNN 가지고 보정하고 이런
we try to refine with the AI the images from the cameras
부분은 제가
and calibrate
다시 뭐
the
얘기하기
devices
죄송합니다만 지금 카메라 기술들이
to fit the
옛날 20년
environment.
전에
The
제가
camera
박사학위를 할 때하고
technology
엄청나게 많이 바뀌었어요.
has greatly
15년
advanced
전에 저는
compared
그러니까
to
그
25 years ago
소를
when I was
남아놓고
writing up
카메라
my
두 대 가지고
PhD
체중 측정하는
dissertation.
알고리즘 만들었었거든요.
An
그
algorithm
불빛
was
측정해내고.
developed
근데
to
지금은
measure
이제
the
굳이 카메라 두
weight
대를
and
갈거 없이
volume,
그냥 카메라 한
but
대로도
now
쭉 다행히 카메라 한
we
대
don't
가지고
need any other
돼지 체중하고
technology
체위를
as long as we have a
측정하는
camera. A camera is
프로그램이
enough
약간
to
부족한 것들은 결국은 이제
measure all of
딥러닝이라는 게
those
나오면서 그런
aspects.
부분들을 다 어느 정도 다
With the
오차를
deep
줄여주는 굉장히
neural learning,
기능이
DLN
있어서
technology,
굉장히
the
다양한
range of
부분들로
error
저희들이
was greatly
확보를
narrowed
하고
down, so it
있고요.
is becoming more precise,
그다음에
and we
오늘
are
저기
seeing
아까
much progress.
탄소 제로 얘기가 좀 있었습니다만은
Well, carbon
요,
neutrality is a
논문
major
같은
topic for
경우에는
today's symposium.
돈사에서 슬러리 돈사에서
This
나오는 탄소 그러니까 온실가스의
paper
양을 추정하는 모델입니다.
looks at how to
모델인데
estimate greenhouse
그래서
gases
이
emitted from
모델을
pig
딜러
farming
모델을
houses.
쓰면서 그게 어느 정도 바닥에서 바닥
So
면적이라든지
we
온도
look at
습도
the
그다음에
Taylor
그
diagram of
그러니까
validation
슬러리
results.
온도까지 그 측정하게 되면
From
적어도 여기에서
statistical and machine
얼마
learning
정도의
models, we
그
measure the
온실가스가
temperature
그러니까
and
나온다 그러니까
it eventually tells us or shows us how much greenhouse gas is emitted.
이것도 마찬가지로 머신러닝 가지고 다
This is all analyzed and calibrated and refined through machine learning technologies.
교수님 말씀하셨던 돼지 얼굴 인식 기술입니다.
This is the facial recognition technology applied to pigs.
들어가기 전에 그러니까 급이기 들어가기 전에 카메라
Before they enter the feeder, they look at the camera.
사실 사람 얼굴 인식하는 거하고
This recognition technology is
지금 뭐
exactly the identical technology used to recognize human faces.
99% 극단적으로 완벽하잖아요.
Well,
그냥
it's not, it may not 100% accurate, but it's close to 99%. I mean, we always have to take off our masks in order to help our phones recognize our faces. Our eyes are not enough for total facial recognition, but still, we apply the same technology to pigs in feeders.
그 먹는 거 자세, 물 마시는 자세 제어하는 거 이거는 큰 건 아니니까.
Well, this is looking at the posture of the pigs when they're drinking water, but it's less important, so I'll skip.
지금 얘기하는 다 논문들은
All of the
딥러닝을
papers, the academic papers, are based on deep learning technology. The algorithms are slightly different, but mainly it's about deep learning. Here, this is a paper on technology that predicts how temperature and humidity will change in the pig farming houses or pig sheds. And here, this is a study on how the amount of greenhouse gases affect the change in pig behavior. That is what the algorithm detects. Okay, I'll move on.
그거 하면서 그게 이제 요게 아침에 이제 역습됐다는
And
논문인데
actually,
일단은 위쪽에 있는 카메라가 얼굴
there
인식이
is a
아니고
camera on
자체로
the
다
ceiling, so
돼지
it not
인식을 알아야
only
됩니다.
recognizes the face,
공사는
but
이제
looking at
외국
the
논문을
whole
쭉 보게
body,
되면
it should be able to
등에다가 마킹을
recognize
하는
or
거예요.
identify the
근데
pigs.
등에다가
So
마킹하면은
if we look at some foreign cases, they put a mark on the back of the pig, but that is not the most optimal way to recognize the pigs.
반대로 앞으로.
If we move up one slide, actually.
그래서 거기에서
One more, thank you.
온실가스에서 눕고 자고
So
먹고
it shows
이것들을
how the pigs
계속
eat, sleep, and lie
모니터링하는 거예요.
down.
그래서 횟수가
We
어떻게 되고 그렇게 하는 시간이
continuously
얼마나 되고.
monitor the behavior and measure the time but
가장 여기서 중요한
it takes them
것은
to change their behavior.
얘가 얘 얼굴 인식보다 얘가 더 훨씬
So
더 중요한 기술들입니다.
Actually, this technology is much more advanced and more significant than facial recognition. there's just one camera on the ceiling, and it should be able to identify and tell apart different pigs from one another. Well, here there are 5 pigs, but in real farms, it will have more pigs. So there is room for improvements, but still, this is a very remarkable technology. So we need more equipment here to perfect the technology. This device is still being developed, but it is an automatic feeder and also automatic water supplier. So 7 environment information and 8 biometric data can all be picked up by this device. Temperature, weight, feed intake, excretion are some of the biometrics data that can be detected.
And with CO2, ammonia, and other environmental factors, they are automatically measured. And this is something we piloted in the last year, and I wanted to add a slide, an updated slide, but I've sent the final version of this PPT slide last week, so I wasn't able to update the file.
자, 하여튼 두서없이 얘기를 쭉 드렸습니다만은 다음
So the conclusion is this.
결국은 동식물이 가지고 있는
Anyways, animals and plants, and since our topic is the livestock industry today, they have something and they have data. And from humans' perspective, we shouldn't interpret the data from humans' perspective, but from animals and plants' perspective. And this kind of interpretation is important, and we do have the technological prowess to allow this. And these kinds of technologies, advanced technologies, can generate profits. In our era and in our times, the signal analysis is important, and we're at this level. And if there are some PhD students here, I suggest you to look into how we can signal our thoughts from humans to plants and animals. I think that this is a problem that we can figure out, and let us take a proactive measure towards all these. Whether we like it or not, computer science is very important, and it has a big role to play. So once again, I would like to emphasize the fact that smart technologies are important in the livestock sector, and people who had plant-related backgrounds, they should learn about computer technologies and whether it is better for computer scientists to learn about plants and animals. That is a question. So which way is better? I think that the latter is better. That's just my personal opinion. Biological experts of biology, it is very difficult for them to learn and become experts of programming language. However, most of the advanced technologies are based on Python and other programming languages. So these solutions, most of them are being utilized and being piloted and experimented in our lab. So if possible, computer science technologies need to be learned by experts of the livestock industry. Thank you so much for your attention. Thank you, Professor Kim. I can feel that I learned a lot about your research. How about we have this Q&A session and receive questions from maybe 2 people, or if we have a Q&A session at the end, we can do that, but he has to leave now, so if you have questions, please do ask. Yes. Yes, microphone is coming. Hello, I am Woo Junpyo from Kagyo. In the pig pen, you showed the pig recognition technology. So what kind of technology did you use to enable recognition? So I provided you with a general information, but regarding specific technologies, I will get back to you to Kagir. But just to provide you with a general information, we make the algorithm learn about the size and other information. Sometimes there is an error, but error itself is a process of learning. So this is a deep learning based algorithm. Thank you for answering my question. And one more person, any more questions? Okay, no question. So I have a question for you. So it seems like all the technologies are developed according to your presentation. And what kind of hurdles are there for commercialization? So basically, what happens in pig pens could be monitored through cameras and sensors. But as I've already mentioned, in order to be adopted in farms, we need more samples. And we only piloted the technology in the pig pen within our laboratory. However, for this to be commercialized, I believe that there are also other factors that we need to take into account. So that's one hurdle that we are facing. And we are trying very hard to increase the applicability of our technologies out on site. And second is about image. I said that we are focusing a lot on image, but now we're using RGB cameras. But to increase the data accumulated, we should try to explore more options for cameras. 2D and 3D cameras could be an attractive option for us. More to that, image plus other technologies need to be leveraged. Diversification of technology is the key. Along with image technologies, voice recognition could be a great option. Of course, voice could lead and could be connected to other disciplines, so we need a lot of efforts, but still, I think integration of technology is important. So you have used a lot of engineering technologies, but now we need the experts from the agricultural industry. Thank you. Next, we are going to invite Professor Louis O. Tedeschi of Department of Animal Science, Texas A&M University.
Professor Tedeschi is a professor at Texas A&M University, and he's a chancellor adjunct fellow at the Department of Animal Science, and an honorary professor at the University of Sassari, Italy. And he is well
Hello,
recognized
my name is
internationally
Luis
for
Tedeschi
his
from Texas A&M
accomplishments in
University,
the modeling
and
nutrition of ruminants. And then he is a really expert in the precision feeding, and one of my best friends. He educated from Brazil, and he originated from Brazil, and then he had his PhD in the animal science department in Cornell University. And in 2020, he a recipient of the Federal Federation of Animal Science Society and American Society of Animal Science New Frontiers in Animal Nutrition Award. And 2013, he was invited to serve on a prominent committee of National Academy of Science, Engineering, and Medicine, which is known as NRC feeding standards in Korea, in the session of the beef cattle nutrient requirements published in 2016. And he recently moved from his expertise into the smart farming and precision livestock farming. So his presentation will be done by the recorded versions. 그래서 레코드를 먼저 들으실 거고요. 그러고 난 다음에 he's actually right there. So he will answer your questions and comments. So if you have some questions or comments, please leave them in the chatting room or QA, and then the audience in the floor can ask questions after his talk. 예, 그러면 레코딩 틀어주시죠.
Let us begin.
Hello, my name is Luis Tedeschi from Texas A&M University, and I'd like to thank the organizing committee for the invitation to talk at the 2021 Towards a Carbon Neutrality on Smart Livestock Farming Strategies. I will discuss some of the smart livestock farming strategies that I see for the United States. I also would like to, at this time, thank my collaborator, Egleo Mendez, who helped me to organize this presentation. So this background, most of you already know this information that world population is expected to grow to 7 billion today, to 9.4 in 2030, or 10.1 to 2050. And other problems include management of the finite resources, such as land, fresh water, and need to reduce livestock contribution to greenhouse gases. We also need to manage highly contextual and repetitive day-to-day routines in livestock management to make it easier to produce animals. And the next issue we need to solve is that the demand for animal source foods in low and middle income countries quadrupled from 1970 to 2012. The demand for animal source foods is still predicted to increase by 35% from 2012 levels by 2050. So the United Nations 2020 report on the planet's health. Indicated that a parallel this up and down situation between sustainable development and climate change. This up and down situation between sustainable development, the 1997 Kyoto Protocol, and the unattainable goals of the 1997 Kyoto Protocol. Meetings and many climate change organized by the United Nations. COPs, most negotiations about climate change organized by the United Nations. Festival of most negotiations at these conferences have given the entanglements generated by politics and betrayals. Given the entanglements generated by politics and hidden agendas, no G20 country has met the 2015 Paris Agreement. Undermining the G20 country has met the 2015 Paris Agreement by undermining the hopes to limit global warming in 2030 by 1.5 degrees Celsius in 2030. How to achieve sustainability? So the question in the livestock industry, more specifically, how to achieve sustainability carbon neutrality in the livestock industry, more specifically, zero emissions, how to achieve a carbon neutrality given all of these different zero emissions that we see here, different issues given all of these different scenarios that we see here, different issues that we have to solve on top of carbon neutral equals to net zero. Is carbon neutral equals to net zero? Sarah and Frank gave us some ideas of this terminology that is currently So carbon neutral being used by the industry and intergovernmental panel. So carbon neutral established by the intergovernmental panel on climate change in which anthropogenic CO2 carbon that the condition in which anthropogenic CO2 carbon dioxide emissions associated with the subject are balanced by anthropogenic neutrality is CO2 removal on a life cycle. That means carbon neutrality is often assessed based on a life cycle. Also established by the IPCC. The net zero carbon dioxide or CO2 means that the condition in which anthropogenic CO2 emissions are balanced by anthropogenic CO2 emissions are balanced by anthropogenic CO2 removals over a specified period of emissions are equivalent. On a global scale, carbon neutrality and net zero CO2 emissions are equivalent. Then there is another one called the net zero greenhouse gas emissions, also by IPCC 2021. The condition in which metric weight anthropogenic greenhouse gas emissions associated with a subject are balanced by metric weight anthropogenic greenhouse gas removals. So net zero emissions by IPCC can be achieved when anthropogenic emissions of greenhouse gas are balanced by anthropogenic removals over a period of time. When multiple greenhouse gas are involved, the quantification depends on the climate metric chosen to compare emissions of different gases, such as global warming potential or global temperature change potential, and others, as well as the chosen time horizon. So the Paris Agreement had a goal to limit global warming below 2 degrees Celsius. There was a preference to be less than 1.5 degrees Celsius compared to the pre-industrial levels. The Kyoto Protocol, as I mentioned in 1997, was focused on greenhouse gas emissions, whereas the Paris Agreement was more focused on temperature change. It is important to understand that the climate metrics fit for purpose in representing temperature change impacts across future emission scenarios. The primary sources of greenhouse gas emissions, GHG, in livestock systems are enteric methane, nitrous oxide N2O, and methane from manure handling and management. The N2O nitrous oxide from feed production as well. The greenhouse gas emissions are reported on a CO2 equivalent basis. It is represented by the sum of all greenhouse gases standardized to a common unit by weighing each gas to a global warming potential, or GWP. The GWP weighing factors were defined by the Intergovernmental Panel on Climate Change, IPCC. And this is how it is computed. The GWP 100 for a specific gas is the mass of that gas times that gas 100-year GWP factor. Most greenhouse gas emissions from cattle production of beef and milk are the non-CO2 gases such as methane and nitrous oxide. This plot shows the contribution of 6 different economic sectors to greenhouse gas emissions on a CO2 equivalent basis. in the United States in 2019. As you can see, the changes are subtle from 1990 to 2018, but the electricity generation and transportation are the major players for this, and second coming industry. Agriculture contributes about 10% of total U.S. greenhouse gas emissions, and livestock contributes about 4% of total U.S. greenhouse gas emissions. Direct livestock contributions to the U.S. total greenhouse gas emissions are relatively small, but directly responsible for 38% of U.S. methane agriculture emissions and 4% of U.S. Nitrous oxide agriculture emissions. Emissions from dysenteric fermentation and manure management direct emissions represent about 41% of agricultural total greenhouse gas emissions. It is very important that when comparing these numbers, we define what are you comparing this against. So this one is what is the contribution of ruminants to the total greenhouse gas emissions. Within the enteric fermentation, beef cattle is responsible for about 72%, and dairy cattle is responsible for about 24%. So if you look at within the manure management, beef cattle is responsible for 15% and dairy cattle accounted for 46%. The remaining of this to 100% comes from other type of livestock production, such as swine. So when we look at this relationship here, this is beef cattle contribution to total greenhouse gas emissions in the U.S. In 2019, beef cattle emitted about 23% of agricultural emissions, and this is what I'm showing here. So you have the livestock species, beef cattle is this group here, 54.4, and livestock is responsible for 21.5 in agricultural activities. Therefore, 54/41 is about 22.6% of agricultural activities. When we put this on a total scale of the U.S., the beef cattle production was responsible for 2.2%, which is 54.4 of 41.5 of 9.6. Agriculture, here in red, is responsible for 9.6% of the total emissions of greenhouse gas in the U.S. So this is the number that we need to think about. Beef cattle is responsible for 2.2%. The beef cattle segments have different impacts on greenhouse gas emissions. There are 7 major regions in the United States that produce beef cattle. These regions are defined based on climate and how the climate and resources, natural and man-made, affect the culture and management practices across the U.S. Most feedlot operations are concentrated here in the central portion of the United States, whereas cow-calf and backgrounding stages are spread around the country. So you find cow-calf all over here, but the feedlot portion is concentrated here in the middle. So when we look at different beef segments and what are their impacts on greenhouse gas emissions, this one is showing that total greenhouse gas emissions in terms of methane. So the green means cow-calf sector, this orange means stocker background, and this darker orange means finishing or feedlot situations. So this is for methane, this one is for nitrous oxide, this is total CO2, and this is the total of all of these different greenhouse gas emissions. So when we look at this data, 35% of ammonia was emitted during the finishing phase, this one here, where cattle are normally confined in feedlots or barns. Over the cattle production life cycle, about 77% of methane emissions was associated with the cow-calf sector, showing here in green. and the major portion of the nitrous oxide from the nitrification and denitrification process in soils was associated with cow-calf production as well, as I'm showing here. So the cow-calf is the one that is actually contributing the most for all of these greenhouse gas emissions here. And these, I have to tell you, these numbers are relative percent of carcass weight. Of course, these animals here in the finishing, they are heavier, therefore there is a dilution effect here. But this is when we put everybody on a carcass weight. But the assessment of greenhouse gas equivalent emissions is not that simple. Greenhouse gases are typically converted to CO2 equivalent using the GWP metric over varying time scales, as I mentioned before. And these time scales are selected to calculate the equivalent metrics that have a significant effect on the final computed carbon footprint. For example, if a GWP 20, meaning over a 20-year time frame, is used, methane is considered 84 times more potent than CO2. But when this is expressed over a 100-year time frame, then the GWP of methane falls to 28. The high heat trapping potential increases with shorter time frames because methane is a short-lived pollutant with an atmospheric half-time of about 9 to 10 years before being oxidized by hydroxy radicals, compared to CO2, which can remain in the atmosphere for thousands of years. This has led some to question the use of GWP 100 to suggest that other metrics, including global temperature potential and GWP star, might be more effective, although both the GWP 100 GWP star are relatively new and lack some policy influences. So here comes the smart farming, livestock farming strategies. So this is based on FAO's 5 practical actions for rapid impacts on livestock emissions. Action number 1 is boosting efficiency of livestock production and resource use. Action number 2 is intensifying recycling efforts and minimizing losses for a circular bioeconomy. Action 3 is capitalizing on nature-based solutions to ramp up carbon offsets. Number 4 is striving for healthy, sustainable diets and accounting for protein alternatives. And number 5 is developing policy measures to drive changes. So all of this lead us to best practice to reduce livestock greenhouse gas emissions, which means, for a practical application, improving feed quality and digestibility, improving animal health and welfare using precision livestock farming, and manure management, collection, storage, and utilization needs to be improved as well. So the question becomes, what is precision livestock farming? Is the application of process engineering principles and techniques to livestock farming to automatically monitor, model, and manage animal production. It allows for real-time monitoring of animals, equipping animals with sensors, ensures maximum use of farm resources, allows us to enable control of health status of animals, and it can assist us to potentially mitigate greenhouse gas emissions. How does it work? Based on decision support systems. We have to use algorithms like machine learning, statistical analysis, modeling, simulation, data mining, it's a lot of data being collected, and develop data-driven decision support tools to assist producers, stakeholders in general, to improve the sustainability of the cattle production or the livestock production. The livestock Internet of Things, as I mentioned here, makes it possible to collect, transmit, and distribute, sense, and analyze data on a massive scale. And the goal is to collect data from different contexts and domains to support the processing of the data and understanding how these factors are affecting the production of these animals and which decisions we have to make to improve the production and sustainability of these animals. For about 60 years in the United States, many livestock experimental data were collected and analyzed, mainly group-wise, reflecting the population samples. Such approaches are still commonly adopted nowadays, though data are more obtained on individual animal basis these days, and consequently, given the surge in the sensor technology initiated back in the 2000s, in tandem with the development, evolution, dissemination of Internet of Things, sensor technology became available in many shapes, forms, and sizes. While the objective of sensors is to clearly collect data, the primary purpose of Internet of Things is to facilitate the transfer of data through a network to be stored in the cloud, accessed remotely, and processed by cloud computing in powerful remote sensors. A humongous amount of data collected and stored by the combination of IoT and sensors gave rise to the concept of big data, and with it, scientists thought the modernization of agriculture could be possible. So big data processing to analyze the information from IoT is the next step, and it's very important. So when we're looking at precision and smart livestock farming, the components include a continuous and real-time collection of sensor data, integration and storage of data, data analysis, machine learning, simulation modeling, and event detection and signaling. With this type of information, we can improve animal health and welfare, which will improve in livestock production. We can have healthy, well-treated animals, meaning superior products, and optimize animal welfare, meaning reduce emissions. The cost of reducing emissions needs to be balanced with the benefits of livestock welfare and production. But the challenges are integration and interpretation of this heterogeneous data coming from different equipment and data sources. So this picture illustrates the hypothetical concept of smart farming that combines livestock and crop production within an interconnected environment. They use sensors all over to ease the decision-making process by the owner, who is at someplace else, far from all of this where the production is happening. All of these sensors are collecting information and sending to a common place that goes back to this computer here that gets processed, and this person here can make a decision. The field of wearable IoT in precision livestock farming is still incipient, but growing quickly. This picture illustrates the possibilities of precision livestock production in smart farms, from disease warning to precise milking production and to precise feeding, or precision feeding as we say it. However, there is a lack of comprehensive analysis and research scheme in the PLF and smart farms from what we call the wearable IoTs. In the field of animal production, considering cost issues, most of the research and applications are relatively scattered and low-tech, such as ear tags, pedometers, which are increasingly unable to meet animal welfare and human quality requirements for livestock products, which means we have to invest more on these wearable IoTs that we can actually assign or give to these animals to collect more meaningful data than what we're collecting right now. The majority of wearable IoT are for humans, likely because of the economy of scale makes it profitable in this market, but not in the livestock or agriculture business. This picture illustrates the possibility of sensors and IoT for livestock production. Physiological sensors need to be integrated on wearable IoT devices or substrates to monitor various indicators and external stimuli through organic biocompatibility technology. Wearable systems for in vivo monitoring is becoming a reality. Sensors used in wearable devices can be divided into what I call biosensors, chemical sensors, and we can actually determine nutrient intake using this physical sensing and vital signs here, and so through biomarkers we can actually detect all of these different hormones in the animal that we are able to collect some of this data. The most important question is what to do with the data. As you can see here, there are many different sensors that we are actually employing. Now we have to make sense of all of the information that these sensors are sending back to the producer, and what we're gonna make with this, and how can we benefit from this. So then the question becomes, what are the opportunities for mitigating methane emissions from ruminant livestock? So we, from the livestock sector, we emit a lot now, but we are a lot more efficient than we used to be back in 1990s. So direct greenhouse gas emissions from U.S. dairy industries, we increased methane emission, enteric methane emission by 11%, manure methane emission by 119%, manure nitrous oxide by 16%. But we require less animals and we produce a lot more milk per cow. So our efficiency has increased. And the annual milk production in the US has increased by 71 billion pounds of milk on an annual basis. So there are differences among systems because of climate and soil factors that are beyond the control of the producers. So warmer and wetter climatic conditions and higher clay content soils tend to increase both carbon and nitrogen emissions. And precipitation variation affects the need for irrigation, the need for water to drink by an animal. Some general recommendations cannot be made at the national level for improving sustainability. Therefore, improvements should be made on an individual operation basis. Consider the factors influencing the management of the operation, the time needed to produce finished animals, feed used to obtain a greater rate of gain or change the composition of the carcass, optimal use of fertilizer and limestone, for instance, minimizing use of trucks and vehicles in the farm or ranch, and efficient use of water. All of these are part of what we call smart farm strategies. So options to reduce methane from livestock include increasing productivity in livestock system, more greenhouse gas efficient animals. FAO estimates improvements on management practices alone could reduce net emissions from livestock systems by about 30%. We need to invest in technological innovations. I'll give some examples later. Feeding genetics, animal health, and general husbandry needs to be improved. Use resources more efficiently. Reduce environmental impact. So this graph here shows the relationship between average emission intensities of greenhouse gases from a national dairy system. Each point represents a country and average productivity of those dairy systems. The two take-home messages here are Dairy emission intensities are vastly higher in countries with low average productivity, and these tend to be the lower income countries. This suggests that significant gains could be made through targeted investment to improve efficiency in systems producing less than 2,000 pounds of fat and protein corrected milk. So these are the ones that are producing a lot of, or emitting a lot of greenhouse gas emissions and not producing enough. Again, this goes back to more greenhouse gas efficient animals or systems. Nutrition and diet formulation has a direct influence on animal production, product quality, and animal health. And we have discussed several times that decision support systems for managing nutrition and diet formulation can be farm specific, needs animal information, feed, and environmental characteristics. We can accurately predict dietary nutrient requirements on an animal basis or a group of animal basis, reduce nutrient accumulation on farm, manure, and nutrient excretion. Deployment of technology that meets governmental regulations by facilitating the application and development of site-specific plans and also use byproducts. And this goes back to what we're talking about. These improvements have to be done at individual basis or a region or a basin, not at a national level, because production systems differ from one place to the next. Minimize nutrient output per kilo of milk or milk produced. I believe that the use of modeling-based decision support tools together with innovative pasture systems in a more integrated smart farming approach could be the next step toward improving the sustainability of livestock systems. System modeling is a powerful tool in the area of nutrition as a whole because it accounts for many variables and the interactions involved in identifying sustainable systems in each situation. It is necessary to combine a range of models from different fields, including animal, soil, crop, and weather sciences, to achieve sustainability. From a nutrition and feed additives perspective, we can actually reduce methanogenesis. Mostly in vitro studies have shown reduction in methanogenesis, but still require in vivo and large scale evaluation, such as a system or base in a region production. There are some technologies that are becoming available that are extremely efficient to reduce methane. This one is a potent inhibitor of enteric methane production and can reduce methane production by 20 to 40%, without changing milk yield and no changes in milk composition. There are other plant-based products too, like condensed tannins, saponins, essential oils that can serve as a methane inhibitor, and some other feeds that we still don't know that they exist, but we are researching them right now to reduce methane emissions, such as Asparagopsis taxiformis. And from economic factors, we have a circular economy, minimize losses and waste management. We need to promote circular bioeconomy. We have spent too much time on this linear process of extraction, production, use, disposal type economy. We need to have some sort of a feedback loop that links this disposal and use back to the production and the extraction phase. So we know that increasing this may have a negative effect that will decrease extraction. We need to recycle and minimize the loss of resources and nutrients. Globally estimated 1/3 of food produced is either lost or wasted. We need to reduce this. Use byproducts as feeds to feed livestock animals. We need to capitalize on nature-based solutions. Livestock farms can contribute to renewable energy production through biogas, solar, and wind power. Soil carbon sequestration through regenerative grazing practices and restoring degraded land can help to put carbon back in the soil. Halting expansion into forest for feed production and pasture, most specifically feed production, soybean meal from soybean production. Mixed crop and livestock systems among trees, like we call the silvopastoral type systems. This is something we need to start paying attention, combining forestry and livestock production, more specifically grazing animals, in the same environment. Not only we can produce different products, but we can also help the environment. And that's what we need to start thinking about. Genetic selection is the key to select individuals that can have a greater productivity. They can match the local conditions, improve the feed utilization and efficiency of use of that feed and energy in a sense. Feed consumption is a key driver of methane emissions. We need to select for feed-efficient animals by measuring intake. Low versus high groups up to 40% difference in feed intake. There are different systems out there, I'm showing down here, that we can assess the dry matter intake of these animals and select, use these are progeny of different bulls, so we can select which ones are more efficient in terms of feed efficiency. Genetic selection for feed efficiency. These are two animals that are extremely similar. They weigh the same, very similar weight. These animals here, they gained about the same, but look at this. These are the expected intake of these animals given the body weight and the average daily gain. But look at this. This is the real intake for this animal here. So this animal here ate a lot less, 123 kilos or less. And this one actually ate 110 kilos more than we were expecting based on body weight and gain. So this animal is less efficient, whereas this one is extremely efficient. So we need to select for this type of animals here. And we can use this type of information here. So this is the average daily gain here on the x-axis. This is dry matter intake here. All of these different quadrants here, we're looking for this one here. Animals that gain a lot and eat less. These are the animals that we should be targeting. So current technologies to assist with growth efficiency include in-pen weighing and water intake systems. These are real-time animal body weight measurements and water intake measurements. So using this technology here, collecting this information of these animals as they come here to eat their diet, their feed, we can actually start selecting which animals are more efficient. So for instance, look at this plot here. So this one here is based on average daily gain. 1, 2, 3, 4 average daily gains was measured at different points here. And this is the predicted body weight over time. We're using a linear scale here. Whereas using this type of system, we can collect the body weight multiple times within a day, and we can have a much better projection of what's going to happen to the body weight of this animal. Therefore, selecting when more appropriately, when is the best days on feed that these animals will have a specific body weight. There are many sensors out there, and I'm showing you some examples here of sensors that we have right now that we can select or use to collect information on these animals. Most of these here for dairy animals. We have these collars here. We can actually measure where these animals are at, what are they consuming, where they're located at, temperature of this animal. These sensors here, we can have an assessment of what is the temperature inside of the animal, what is the ruminal pH, rumination time of these animals, We can have sensors that measure chest sounds. We can use these to also determine rumination of these animals, and we can actually use this to detect disease and so forth. So these are also other sensors used in computer vision. We can actually determine when animals are need some sort of antibiotic treatment. Animals that we can assess what is the growth of these animals by using this computer vision system here. What is the conformation of the body of these animals and so forth. What is the water level, if the quality of the water that these animals are drinking, the temperature of the water. This one is another sensor, another technology, computer vision technology, that we can actually measure how these animals are moving, if they're having some sort of problems like laminitis, or if they're having any other source of problems because the movement of these animals are not ideal or not standard. And this type here is integration of many different sensors into a type of a software or decision-making system. So in essence, this plot here is showing you all the different layers of devices and software apps that are needed to manage all the data that is being collected through this IoT, Internet of Things, and sensors all over. So the question is, why so many data records? The thing is, given the type of information we're developing these days, we really need to have big data to develop the systems that we're planning to develop to manage these animals. From a mechanistic modeling to a machine learning type application. So we're moving away from this type of modeling that explains the concepts or the mechanisms behind when something affects something else, and we understand this really well, or at least these are the concepts of what we believe, our perception, or what is happening in real life. We're moving to things like this, more machine learning process, that we collect large amounts of data and we develop specific systems to interpret that data and provide outcome or prediction of what we believe is going to happen next, or forecasting in essence using machine learning. That might be a problem. So challenges I see for smart livestock farming: protocols and methodologies to measure greenhouse gas emissions. We have long-term effects, research, multiple environments, validation. We have to make sure that we understand that the protocols, the methods that we are using can be used to compare different production systems. Protein demand to support population growth. That is, we know the population is growing. That is a requirement to produce more meat, and we need to do this on a sustainable way or through sustainable systems. And we need to produce low-cost products. So those are the two key things here: sustainable production, low-cost products. And we need to be aware of the circular economy, maximum use of all resources, and also be aware of the effects of what is the product at the end, how it affects the beginning. And land use restrictions. Waste management, we need to improve our waste management of soil, water, food, and products in the sense. We need to adopt different technologies by livestock producers. We need to sell these ideas to them and be similar and be cohesive when we're selling the idea to producers. That is a data integration from multiple sources, and we need to integrate this data so we try to understand from all different aspects or different viewpoints in terms of the production. And technology changes. It will change, and we need to be aware of those changes in real life. So, climate change is a global problem that demands well integrated solutions at local, national, regional scales, but we have to be aware that the solution for that might be different for specific situations. So that takes me to some of the summary of what I've been talking to you today. The contribution of livestock, specifically ruminants, to greenhouse gas emissions is variable across countries and within the country. Each country should enable different strategies to achieve carbon neutrality, which means the amount of carbon being produced or emitted by animals is the same amount of carbon being mobilized. Smart livestock farming is the next generation of tools for sustainable livestock production, specifically ruminant animals, and I'm listing cattle, sheep, and goats, but all animals are included in this smart livestock farming. Data generated by multitude of sensors and Internet of Things should be analyzed using artificial intelligence, because that's what AI does. It's the best option for that. However, mechanistic concepts of livestock production should be part of the process, so we don't forget about what are the mechanisms behind what is happening in real life, so we can try to understand what is this artificial intelligence telling us to do. Compatible systems like sensors, IoTs, AI programs, and standardized methods must be developed to allow for the comparison of different production systems, not only within a country but also at different countries and different production systems or different scenarios of production. Thank you. Hello, my name is Luis Tedeschi from Texas A&M University, and I'd like to thank the organizing committee for the invitation to talk at the 2021 Towards a Carbon Neutrality on Smart Livestock Farming Strategies. I will discuss some of the smart livestock farming strategies that I see for the United States. I also would like to, at this time, thank my collaborator, Egleo Mendes, who helped me to organize this presentation. So, this background
cow-calf management.
Louis, hold on, please. The audience cannot hear you. Just technical issue here. So just continue. Continue, say. No, not yet.
Hello, my name is Luis Tedeschi from Texas A&M University, and I'd like to thank the organizing committee for the invitation to talk at the 2021 Towards a Carbon Neutrality on Smart.
Yeah, technicians are trying to solve now, so just wait a minute, please. Can you say one more time, Luis?
Yeah, hear me now?
It's better.
Okay.
Yeah, just go ahead and just go ahead, Luis.
Okay, yeah. So thank you for the question. It's a very valid question. Can you hear me now? Larry, can you hear me?
Yeah, at least I can hear you. So you can say. Yeah.
Okay, so I'll say quickly, and then you can translate or tell to the audience. There are sensors in the beef cattle. The problem is this: what is the profitability of investing in sensors in the cattle, mainly in the cow cat? It's very different than investing in sensors in the dairy unit. It's almost like you don't have a lot of sensors for the calf. You have a lot of sensors for the dairy animals and so forth. So in the beef unit, most of the sensors are related to feedlot units. So you have a lot of these sensors actually measuring location, where those animals are located at, measuring weight of these animals, measuring temperature of these animals, and actually measuring the water consumption of these animals. In the beef cow, you also have some sensors like pregnancy, temperature, forward, locating those animals and where they're grazing. But again, it goes back to how profitable it is, and if it makes sense to be more on the beef, and which sector of the beef. Other sensors are also being used to detect quality of the pasture. And there are some sensors right now that some of those sensors are attached to the animal, to the grazing animal, and then it measures the quality of the pasture on the fly.
닫아주셔도 돼요. 제가 들었으니까. 예, 괜찮아요. 그러니까 지금 소리가 작아가지고 잘 못 들으셨을 텐데 일단은 한국하고 미국하고의 가장 큰 차이점 중에 하나는 비프, 그러니까 소위 말해서 유구 시장이 그 넷 마진이 굉장히 작기 때문에 그 한 마리 한 마리에서의 소득이 우리하고
small in the U.S. compared to us. So what Professor Tedeschi is saying is that the technology is actually similar for both dairy and cattle, but due to the difference in margin, it's difficult to leverage for this cattle sector. So I forgot the word, but there is a technology that can be used for management, but actually it's all about the money and how much profitability the technology can rear from the different sectors. Do we have any other questions from the floor? About 3-NOP, he mentioned it in his presentation, but it was just published and is now just being released. But I think recognition is working, and could he elaborate on how that works?
Can you make a comment on the 3-NOP to reduce the methane emissions? 3-NOP. Not quite well. Actually, I didn't hear you the last part of the talk. What was your concerns about longevity and what was the other? Okay. 지금 사실 그 3NOP에
So,
대해서
to sum up
직접적으로
his answer,
실험을 많이
there wasn't much experimentation on the 3-NOP technology itself, but on that topic, I think Professor O will be more specialized. But what he is saying is that if we look at the results about experiment on 3-NOP, it was very effective for reducing methane emissions, so there is much potential when it comes to that technology for that purpose. But we saw the longest effect using that technology, but we are unsure about the longevity or sustainability of the effect. And decrease of methane means there is remaining hydrogen, and what impact will that hydrogen have? That is a remaining question. So there is a variation in the effect, and those are some of the concerns that he mentioned. But, well, there is definitely potential. Some proof was shown in some country in the world, but not in Korea. It was approved elsewhere in the world, but not in Korea.
Yeah. So can you make a guess how much the greenhouse gases can be reduced by using the precision livestock farming technologies? Can you make any guess? Okay, can you so you mean total 30% in total, right? Okay. Okay. Okay, sounds great. Thanks. 그러니까 지금
As briefly mentioned, according to the UNFAO, precision livestock feeding, precision feeding, and relevant technologies, when only those technologies are leveraged, we can expect 30% reduction in GHG emissions. But in addition, if we add 3NOP or Asperger's feed taxonomy as feed, if we develop those technologies and incorporate those, then we can additionally reduce greenhouse gas emissions. Well, we are well into our lunch break now, so we'll close this session here. Thank you, Professor Tedeschi.
하겠습니다. 예, 그러면 뭐 시간이 많이 지났는데
Yes,
경과됐는데 오늘 일부 순서 함께 해주셔서 감사하고요.
We
예,
went a bit
여기서
over
마치는
time,
걸로
but thank you for
하겠습니다.
joining us
예,
for the first
안내가
session,
또 있을 것
and
같은데, 그죠?
I believe the MC will let us know about how the lunch break will proceed. Thanks.
네, 지금까지 축산 분야 스마트팜 추진 방향에 대한 세션을 가져봤습니다. 이번 세션에서 좌장으로 수고해주신 서성원 교수님, 그리고 열띤 강연을 펼쳐주신 김현태 교수님, 루이소 테데스키 교수님께 감사의 말씀 전합니다. 이것으로 심포지엄의 1부를 마무리하도록 하겠습니다. 이제 중식 시간을 갖도록 하겠는데요. 2부는 오후 1시 반부터 시작됩니다. 모두 1시 25분까지는 꼭 착석을 완료해 주시기 바랍니다. 1시 반부터 2부의 순서를 진행하도록 하겠습니다. And now we will wrap up the first part of symposium. We will have lunch time from now, and second part will begin 1:30. Please come back to your seats by 1:25. Thank you. 여러분 모두 식사 맛있게 하시길 바랍니다. 저는 2부에서 다시 인사드리겠습니다. 감사합니다. 지금부터는 두 번째 세션인 탄소 중립을 위한 유럽 축산 분야 스마트팜 주요 기술 현황에 대해 중앙대학교 김준모 교수님께서 좌장을 맡아 진행해 주시겠습니다. From now on, Professor Junmo Kim of Jungang University will be the chairperson of the second session, Current Status of Major Smart Farm Technologies for Carbon Neutrality in the European Livestock Sector. 이번 두 번째 세션 또한 두 가지 주제로 진행됩니다. 먼저 첫 번째 주제인 유럽 및 네덜란드의 축산 분야 스마트팜 주요 기술 및 발전 전략을 네덜란드 바헤닝언 대학교 농업기술그룹의 마르율레인 델크스 교수님께서 맡아주시겠습니다. 다음으로 두 번째 주제인 오스트리아의 스마트 축산 주요 기술 소개 및 발전 전략을 오스트리아 스마텍 크리스 하워스 최고 영업 책임자께서 맡아주시겠습니다. This session will also be held on two topics. The first topic, major technologies and development strategies for smart farms in the livestock sector in Europe and the Netherlands, will be preceded by Professor Marjolein Derks, the Professor of Farm Technology Group, Wageningen University of Netherlands. The second topic, introduction of Austria's major smart livestock technologies and developmental strategies, will be handled by Chris Howers, the Chief Sales Officer of Austria Smartech. 먼저 이번 세션의 좌장이신 김준모 교수님을 모시겠습니다. 여러분 힘찬 박수로 맞이해 주시기 바랍니다.
Thank you. Hello, everyone. I am Kim Junmo of Jungang University. I am also a leader of the livestock farm in the Ministry of Agriculture, Food and Rural Affairs. Because we are short on time, let us begin swiftly. As our MC said, in the second session, we are going to talk about current status of major smart farm technologies for carbon neutrality in the European livestock sector. As we are having a technical problem here.
네, 진행해도 괜찮을까요?
Yes, sir. Please proceed. No. Could you please wait
처음부터요?
for a minute? Okay, can you start
네,
from the beginning?
안녕하세요. 중앙대 동물생명공학과
Hello,
김준모입니다.
I am Professor
동시에 저는
Kim
농림
from Jungang University. I am also the director of the livestock farm in the Ministry of Agriculture, Food and Rural Affairs. Thank you for your invitation. Let us begin our second session. The topic for the second session is current status of major smart farm technologies for carbon neutrality in the European livestock sector. Two presenters will talk about this topic. As you may all know, Europe has spearheaded the efforts related to carbon neutrality, abatement, and technological development from a few years ago, and they are fully leveraging these technologies. I hope that you can hear a lot of insights from the two presenters. Our first presenter is Professor Marjolein Derks from the Netherlands, Wageningen University. She has majored in veterinary science, farm and animal husbandry from UU. So is the speaker ready to speak? Professor Marjolein is here.
Good afternoon here.
Oh, yes,
All
I'm
right, all
sorry.
right.
Yes.
All right.
Good morning for us, but good afternoon
All
for
right,
you,
thank you.
indeed.
Good morning. So, are you ready to start your seminar today?
I am, I
And
think.
can you
So,
hear clearly here? Can you see our audience?
I see you, and I see
Only me.
the
All right.
screen behind you.
Okay, okay. When you're ready, just please
Yeah.
start. All right.
I think I can share screen.
Can you share your slide at this moment?
I can, yes.
All right. But I cannot see your slide now.
No, I'm
So-
trying to share it now, but it's not working,
All
unfortunately.
right. Just 화면 쉐어가 됐나요? 포스트로? 아, 예.
Oh, it's not working. Give me 1 second,
All right.
please.
No worries.
I have to quickly restart. I'll be back with you in 1 second.
Okay, okay. Can you find the share button? 잠깐 나갔다가 다시 들어오신다고 하니까요. 기다려 보시면 좋을 것 같습니다. Okay.
Good morning.
All right.
Can you hear me?
Yes.
Good. Let's see if it works now. I
Okay.
think so.
So now you can share your slide.
I think so. I have to give permission.
All right. It's properly worked. Okay.
Good.
All
That's
right.
good to hear.
Yeah. Thank you.
So I'm sorry for the delay. Good afternoon, everyone. Thank you for having me here. I'm very honored to be able to give you a presentation. My name is Marjolein Derks. I'm from the Farm Technology Group of Wageningen University. And today I would like to speak to you a little bit about precision livestock farming, and then especially the state of the art, the challenges and opportunities in Europe, but also the potential challenges and opportunities in South Korea. So a little bit about myself. I'm actually trained as a farm animal veterinarian in Utrecht University. And I always wanted to be a veterinarian, but I became allergic to animals when I almost graduated. So in the end, I didn't become a veterinarian. And instead, I went to do a PhD at the veterinary faculty about the socio-economic benefits of veterinary advice on dairy farms. And after graduating, I spent some time in France and in Sweden modeling the fertility in dairy cows using progesterone measurements. And when I came back to the Netherlands, I applied for a position at the Farm Technology Group, where I work now also as an assistant professor. And I work on the design of complex agricultural systems. So that means that we aim to develop novel systems, but our group in itself is really focused on farm technology. So we work a lot with sensing, with robotics in both animal farming systems, but also in greenhouse and arable systems. I have some experience in Asia, but not in South Korea, unfortunately. Here on the left, you can see me in Bangladesh with some of the Bangladeshi female students. I did a project there about introducing buffalo. In the middle, you can see a fish pond in Indonesia. We have a project currently running in Indonesia where we aim to implement smart farming technologies in fish and dairy industries. And on the right, you can see me in Bhutan with our Bhutanese PhD student with whom we worked on the welfare of yak in free-ranging systems in the Himalaya. So a little bit about the Netherlands. The Netherlands is quite a small country, as you can see on the right, and it's located in the west of Europe. So the red dot on the map, that's the Netherlands. And given that it's a very small country, we still do have a lot of people and especially also a lot of animals. So we're with 17 million inhabitants at the moment, and we have 3.8 million cows, 12.3 million pigs, and 101.7 million chicken. So you can see that this is quite crowded. And this immediately gives us some challenges because we have a large emission of nitrogen, especially in the form of ammonia. Due to limited space, land is scarce and very expensive, meaning that farmers aim to intensify their farming systems. Therefore, there is high pressure on animal welfare, and also in our society, animal welfare is very important. So there's a lot of pressure on farmers to include animal welfare in their systems. And we are an exporting nation. We export about 70% of what we produce, and we export that to world markets, and these markets can be volatile. So it's not always sure that you will get the price that you expect for your products. And on the right, you can see a farmers' protest from last year because our government really wants to diminish the impact of farming on the environment. And they are putting a lot of regulations on the farmers, and the farmers were fed up. So at the moment, we really have a very polarized discussion between the farmers and the government about the environmental impact of farming systems. And that means that we have a very high pressure in our country to innovate. Here you see Frans Timmermans. He is a Dutch representative in Brussels, so working for the European Union. And he has presented the Green Deal strategy with the farm to fork strategy behind it. And that's really focusing on diminishing the environmental impact of farming. So higher biodiversity, more organic farming, lower use of antibiotics, but also pesticides and artificial fertilizers. And this strategy will really have a high impact on Dutch farming systems. So we really have to become more sustainable in the future. And if we then focus on animal production systems, there are a couple of trade-offs that we see that are difficult to overcome. So if I, for example, talk about the aspects of animal farming systems, there are different things that we want to improve. For example, the animal welfare component, but also the economy and the environmental impact. And often these things bite each other. So here on the right, you can see two images. The one on top is a battery cage system that we used to use, where animals were really confined in a battery. And from an animal welfare perspective, this wasn't a very good system. So we have shifted to more free-ranging systems, as you can see here on the lower picture. However, the environmental impact of these systems is much higher, even though the welfare is better. So by improving the one, it seems like you are diminishing the other. So one question we ask ourselves is, can precision livestock farming technology provide an answer? And here is one definition given for precision livestock farming. And the main thing is that it uses the principles and technology of process engineering, automatic monitoring, and related physical processes of the animal to try to understand how animals fit in the environment and how we can improve their lives. And that's really what I want to talk to you about today. And I want to start really with giving you some examples of the state of the art. And I want to go there from identifying things in animals to better understand how animals work, to actually utilizing the animal in the system. And the picture on the right is one such example, but I will go deeper into that in a minute. I first want to talk about identifying different parameters in animals and how we can use technology for that. Now, I know that you in South Korea are extremely good at developing technology, sensor technology, but also other technologies. So I guess I'm not telling you anything new here, forgive me for that, but I still wanted to take it into account in my presentation. And I want to show you some technologies we've been working on as a group. And the first one is the automated assessment of dairy cow body condition scoring. We used 3D cameras for that. You can see the papers that were published here on the left. And what happens is that we aim to identify the body condition, so the body dimensions of a cow while she is in the milking robot. So how it's currently being done, it's not automated. You can see on the right a cow and the skeletal parts of the cow that you can visually identify from outside the cow. And what's being done is that the person who is scoring the body condition can see the skeletal processes and can identify how concave or convex they are, and therefore say something about how fat a cow is. And there is on the left a scoring chart that you can use, but what we see is that it's not always very reliable. Different people identify a cow differently based on this scoring chart. So what we try to do is to work this out with image processing to see if we could actually identify the body condition of a cow using image processing. So on the left, the top left, you can see the original image where there is the cow body surface, and that is then processed, as you can see on the right, to identify the height really of the different processes, and therefore how concave or convex the shapes are. So we use the raw image, then we use an orthogonal, I hope that I pronounce it right, decomposition, subtract the background, remove the noise, and then interpolate the point cloud. And what we then get is a 3D image of the animal and an assessment of the body condition. And now you see an image where we can see the results at herd level. So here on the left, you see the predicted body condition score and the manual body condition score, and you see that there's quite some overlap. However, between 3 and 4, there is some uncertainty. And the question is whether that is because the algorithm is not yet perfect, or whether the visual assessment is actually not perfect, and I will continue about that in a bit. And here on the right, you can see for each of the features how well they are being identified by the algorithm. And in the end, the body condition score, we can estimate it with a certainty of 72%, with a mean error of 15%, and for the weight, the root mean square error is 41.2 kilos, so we can assess the weight with quite good accuracy, with a mean average percentage error of 5.2%. Then I go to a next example, which we are currently working on, and it's plumage condition in white hens. So what you see here is our experimental setup. We have a Z2 camera placed on near the feeding line, and we are collecting images of chicken. And we score these we score their feather condition. So we score their feathers as 0 being very good, 1 being suboptimal, and 2 being bad. And we score them visually, and then we have the algorithm identify the score. So we trained the algorithm based on human observations. And here you can see what that looks like. On the left, you see an image with only one hen. So this is a hen, and the score of this hen is 1.5. So we have both the score for whether it's a hen or not, and then a score for the hen plumage condition. And we can also work the algorithm if there's multiple chicken in the scene. The paper describing this algorithm will be published soon. And then a bit about how well we can do this. So what you see is that if a hen has been given a score class 0, so no feather damage, we can correct that with the algorithm. We can predict that correctly with the algorithm in 91% of the cases. But for 1 and 2, you can see that it's not yet perfect. We are currently working on improving the algorithm there. And what, in the end, we aim to do with this work is to be able to identify and re-identify individual chicken in the poultry house, because then we can actually see how a chicken is moving through the house. And one of the things we also really want to know is which hens stop laying eggs or start laying less eggs during the round. So what we see is that during the round, the number of eggs is decreasing, and we're not yet sure whether that is individual birds who stop laying eggs or whether it's less eggs per hen. And that would be something that we could identify if we were able to track the animal in the system. So now that we have a lot of measurements about these animals, can we use those measurements to better understand how animals work in the system? So here, for example, you see a picture of an experimental setup where we try to estimate heat stress in cows. Now, I know that also in South Korea, you have to deal sometimes with extreme weather events or high temperatures, cows cannot really stand those high temperatures. So what we aimed to understand is how a cow responds, both in terms of respiration rate, and high body temperatures. And we used an experimental setup, as you can see here on the right, a climate-controlled respiration chamber. We used 20 lactating cows, and we had a couple of treatments. So these treatments were either a change in relative humidity, a change in temperature, so increasing temperature through time, and using a fan, yes or no. And here on the left, you can see what it looked like. So the red, the blue, and the green lines, they are the different relative humidities that were used for the different trials. And the temperature is increasing, as you can see here below, every day. And there is a day-night rhythm in it. And on the right, you can see for one day what it looks like. So the temperature goes up during the day, and then the relative humidity goes down during the day. And here you can see some of the results. So what we see is that the respiration rate is increasing with an increasing ambient temperature, but that based on the relative humidity, you can see, so high, medium, and low, you can see that the cow starts panting earlier, so with a lower ambient temperature already. And here you can see the same, but then for the, I forgot. Sorry, I forgot what AV means. I will look it up for you. So now we better understand how a cow deals with high ambient temperatures, but also we want to understand how a cow ruminates her feed, and that's actually the next thing we are currently working on. So part of this has already been published, because we have identified that you can actually see the rumen and the movements of the rumen. So the rumen is the stomach of the cow that really processes the feed. And we can capture it on a 3D camera. So on the right, you can see a 3D image. And we found out that it was possible to identify the rumen motility using a 3D camera. So here you can see the contractions of a cow. And in the end, we had 20 cows with 261 contractions, and we were able to identify those contractions with a sensitivity of 97%. And the cool thing about this is that before we weren't really able to identify rumen motility other than by doing it manually, where you would use your fist to push into the rumen of a cow and you could feel the contractions. But we knew that by pushing our fist inside the rumen, that would give a reaction in the cow, and therefore the contractions would change slightly. Now we actually have a way of identifying these rumen motility without having to touch the cow, and therefore without interfering with the signal, really. And by knowing the rumen fill and the rumen motility, we can really say something about how feed is being processed by the cow. Then the next thing we are working on is, what if the algorithm is right? So, just checking my time. If the algorithm is right, that means that we say that the algorithm is better at scoring than we are. So I told you before already that sometimes we have a gold standard, like with the body condition scoring, but also with the feather condition in chicken. And we know that different assessors identify different chicken differently. So sometimes one person can say this is a score 1, and another person can say this is a score 2. So therefore the gold standard isn't always perfect. And we try to turn it around and say, what if we have an algorithm that is able to classify those birds, and the algorithm is actually working better than the human observer? And this is an assumption, of course. That would mean that we would need a different way of evaluating those algorithms. And the idea is to have the algorithm classify the animals and then follow the animals in time to see if actually those animals develop the symptoms that we expect them to develop based on whatever you are classifying them on, to see if we actually need the visual observation as a gold standard or whether we can skip that in the future. So now I get to the interesting part where we aim to utilize the animal. And as I told you before, this is the work of one of my colleagues, Ellen van Wegel, and she is really working on the role that the animal can fulfill in the system. So we use a very technical perspective, the brief of capacity. So in technical science, you work with functions of the system and you have requirements for the system. And the function in this case would be locomote oneself. So the fact that an animal has to move from A to B to perform different tasks, that is what we use in the system. I hope it's clear. If it's not, please let me know. So in this case, the capacity of the animal is to locomote oneself. So as I said, this means that the animal is actually moving from point A to B. There are different specifications. The animal can move forward, backward, sideways, but also up, actually. And there are different behaviors that an animal can show. So depending on what animal it is. And the associated needs are locomotion. So the external conditions, what do you need for the animal to be able to move around? Is space, surface, and objects. There are subjects, especially in case of group performance, and the internal conditions that an animal needs are a locomotory apparatus, of course. It needs to be able to move, and there's variation in speed. Now, what you see here, one of the problems that we have in current poultry housing systems is that we have a lot of fine dust. And this fine dust is mainly there because animals, they stay in the house and they, of course, defecate. And when this defecation, this feces is drying, then it becomes really dry and fine. And when the animals start showing their natural behavior, with this, which is in this case dust bathing, there's a lot of fine dust coming out. And we are currently not really able to deal with this fine dust. So what Alan designed is this unit where the animal has to go in from below. There's sand here, so the animal can perform her dust bathing behavior. And in order to be able to go out of the dust bathing unit, it needs to fly up. So it has to fly and flap to get up to the stage where she can go out. And by actually flying up and flapping the wings, the animal is able to, is already losing the majority of the dust. And then in the actual poultry house, there's a lot less fine dust being produced. Here's another example of what we are working on. It's the pig toilet. So I'm not sure how familiar you are with ammonia emissions, but if you mix urine and feces together, then you get ammonia. And we are currently aiming to work with systems that actually separate the urine and the manure. And there are a lot of fancy stuff, equipment like belts or different floor types, but they are prone to, well, for example, the technical elements, they can be broken and it's difficult to change them because often they are under the floor. So we needed a system that was simpler. And pigs are actually animals that prefer to defecate in one place. And we designed a system where the animals have some sort of shelter by the gates, but still can see each other. And they will use this pig toilet to defecate. And if they defecate at this designated place, that means that we can remove the manure easily and also separate it from the urine. And by using this system, we can actually diminish the ammonia emission by at least 60%, while just using the natural behavior of the animal, namely that it's prone to defecate on one designated place. Then an example that I would like to show you is the Windstreek house. It's a broiler house. You can see that it's natural daylight. It's also natural ventilation, but that's not what I want to talk about. I want to talk about these things that you see here on the left. So this house is naturally ventilated and therefore the temperature is not regulated. And especially if the broilers are very small, this can be problematic. So what we did was we designed a system here, the things you see here on the left, they are heating plates. So there's heat coming from these plates. And by using these heating plates, the animals can actually themselves choose where they want to be. And what you see is that when they are very small, they are underneath the heating plate, so they are warm there because it's a closed environment. But when they grow taller and they become more self-sufficient in their heating, they tend to move away from those heating lamps. So the animal can choose to be under the lamp or a bit further away from the lamp. And what you see is that when the chicken are growing, they take more space. So they move further away from the lamp. And you really use the chicken's preference for a temperature to spread the chicken over the surface area. So in the beginning, they're all under the lamp, and you see that they, at some point, start to work out their own homeostasis and move away further from the lamp. And that way you can have a naturally ventilated house with open sidewalls, but you can also maintain the temperature of the chicken by allowing the chicken to be under the lamp if it wants to. And the final example that I want to show you is an air circulation, recirculation system, where the heat of that is produced by the pigs is actually being retained in the system. And it's a cooperative project between Wageningen University, but also Korean universities. André Arning, my colleague, is involved in this project. And the air that is coming from the pig house is actually being recirculated, being cleaned, and then being conditioned and brought back into the house. So not all the heat that is produced by the pigs is actually lost. So it's a very, very sustainable system in terms of energy use. And you can see, you can see here that there's an air scrubber in the beginning, and then here using UV light, the microorganisms are being killed. Then it's mixed with fresh air, and the pigs are, well, the pig house is ventilated again. So that's about the state of the art. I also want to talk a bit with you about the challenges that we face, because there will be challenges. So here I show you an example of a journal paper about the use of alerts. And then what you see here, this is a disease alert for mastitis, I believe, that only 55% of the alerts that are given to the farmer were checked upon, and that sometimes only 20 or less % of the alerts were actually acted upon. So they checked, and in many times also decided not to do anything. So we can get a lot of sensor information. We can use that information to build alerts for the farmers, but then to get the farmers to actually act upon the alerts, that's another thing. That's really difficult. And in this paper, they describe reasons for farmers not to act upon alarm. And one of the things that was perceived as very annoying is the number of alerts occurring per day. So if there's a lot of alerts in one day, farmers tend to not always follow up on alerts. So the way information is being presented to farmers is extremely important. So it needs to be clear, concise, well summarized, and the farmer needs to be able to do something with it. So here you can see a screenshot of the NADOP system, the health and management system, where they show the different steps, the different stand-up counts, and the lying time for calves. Unfortunately, I did not find an image where there was really something off, so this group is actually doing quite well, as you can see. But this is, I think, a good example of a clear and easy system to use, because you can really see the differences per day. So here is some work I did on the follow-up on alarm, and these graphs are maybe difficult to understand, but I will explain them to you. So what we had was cows, and we had progesterone values for those cows, and farmers were alerted at the moment that a cow, after she had given birth, was back to being fertile. So what you see is the orange line for each cow, the moment that she was let me put it this way. So we knew when a cow was back in estrus, and we also knew when she was inseminated. And the system that the farmers were using, they were given an alarm at the moment that the animal was eligible for insemination. So that's after the first estrus. And here we group the cows based on the moment they were inseminated first. So this is the cow number, and here are the line is representing the moment or days until first insemination. So cow 1 was inseminated on day 43, and the last cow was inseminated at 145 days after calving. And then the blue line is showing the moment the cow received an alarm for first estrus. So the distance between the blue and the orange line is actually the voluntary waiting period. So the period that the farmer waited after alarm. And you can see in the left farm, the farmer is really acting upon alarm. So he is actually inseminating the cow shortly, for most cows at least, shortly after they receive the alarm. But on the right farm, you can see that there is quite a distance between the blue line and the orange line. And therefore, the farmers wait really long with inseminating the cow after the alarm has come. And then the question is, so I don't mind that they wait for an extra 30 days, but the question is then, why did the farmer invest in a system that can tell him when a cow is in estrus if he still decides to inseminate his cow based on probably a voluntary waiting period of 80 days? So that's a question we had, and we didn't find an answer to it yet. And here is another image of where we grouped. So the 1, 2, 3, 4, 5, 6 on the bottom are the farm numbers, and on the left you can see days after alarm. And the advice is to inseminate a cow 2 days after you received the alarm. But what we see is that farmers do not always follow the advice. There's a large spread. Some farmers inseminate the cows 1 day after alarm, like the purple farm. Some are more around 2 days. I think farm 5 is the majority of cows is inseminated around 2 days. But for some farmers, you can also see there's a large spread in the time between alarm and actually acting upon alarm. And if you don't inseminate the cow around 2 days later, the chances of her being pregnant become smaller. So we also see that the accuracy of acting upon an alarm is not always very high. So we argue that there is a need for a communication of the results between farmers, but also with advisors. We need to make sure that farmers talk to their advisors about how to use the alarm. Because we saw that farmers are willing to invest in expensive systems, but then sometimes don't use the system as they are supposed to, and therefore become very unsatisfied with the results of the system, and maybe advise other people not to buy it. Maybe they stop using it, and that's not what we want. So we can develop perfect technology, but we also need to make sure that farmers know how to use it, and that we check whether the technology is being used as it's supposed to be used, and that it's actually delivering what it's supposed to deliver. And as you could see in my previous examples for the progesterone measurements, probably not all cows would be pregnant in time, or based on the moment of insemination. And the farmers might say that that is because the system is not working, but that might not be the reason. It might be bad use of the alarm. A little bit about reasons for technology to be taken up. So we can develop the technology, but what makes farmers buy this technology? And what we see in the literature is that farmers are much more willing to start using a technology if there is a subsidy. However, we also see that if the subsidy at some point stops, farmers stop using the technology as well. So the uptake is increased by subsidies, but then if the subsidies stop, then the use of the technology also again diminishes. One very important thing that farmers need to get acquainted with the technology is access to support. It's very important to support the farmer in showing him what's available, showing him what it can do, but also support him, as I showed you before, after he bought it and starts buying it. And the question is, of course, what's the added value of this technology? How can I use it on my farm? The project I told you a bit about in Indonesia also includes this, and it works with social systems theory, because what we found is that farmers in Indonesia are willing to use smart farming technologies. However, the system is more or less against them, because what happens is that farmers deliver their milk to milk collection centers, and there is no added benefit if your milk is of higher quality. So even though we want the farmers to produce milk of higher quality, there's currently no bonus for milk of higher quality, and therefore farmers are willing to test and take up new technology if it's being paid for them. But as soon as the financial incentive drops, then they also stop using the technology because they are not getting a better milk price. So I hope this works. Let's see. Can you see the video?
Did you
Can you
try
see
to
the-
learn the video? We cannot see now.
Okay, wait, let's see if I can do it differently.
I think you better to share whole of your screen.
Can you,
Yes,
can you
yes,
see
like
the-
that. Okay.
Yeah, is it
Yes,
working?
yes.
Okay, so I'll talk you through this video because it's in Dutch, and I'll only show you part of it. And in this video, it's we see a system for pig industry where the farmer doesn't have to walk through the pig house, but the pigs are coming towards the farmer. So it's based on hygiene and the fact that farmers, you are supposed to walk from young to old animals. I mean, you probably know everything about the lines and the ages and the walking lines. And this system is developed. So what you see here, the white trays, they contain animals. And they are being brought to the farmer. Then the farmer can check the animals. They are weighed, and the manure is being weighed. The manure is being removed. So we will see an example soon. So here's the dock. That's where the farmer stands. Then the system is telling, the farmer is telling the system which pigs he wants to see. The pigs are behind the wall. So here, I think the system should now, it's a bit slow maybe. Let's see. Here are the pigs are coming. Well, there's no pigs in the system now, but you have to think them there. It's just to show how it works. So they are coming from the part behind. Then they are being moved towards the dock. Here you can see that. They are being turned, and then they are being moved towards the farmer who is standing on the dock. And here the farmer can check the animals. The manure is being removed and weighed, so you know exactly how much manure was produced. And also you can clean the tray, so the animals are in a clean environment again. You weigh the animals, and then here you can check the animals. So now watch closely what happens next, because this is the most important part of the video that I wanted to show you. Because what happens is there's the piglets in the system, and the box is being tilted so that the piglets are actually rolling towards the farmer, and he can easily check them. So the problem with this system was that this was on YouTube, and it was seen by an animal welfare organization, and they were extremely upset about this video. So the industrialization of animal farming systems, it was not good. There were questions asked in our parliament, and in the end, this system that had been completely developed, it has cost millions to develop this system, was not taken into production because there was a big stir from animal welfare societies. So let me see if I can get back to my presentation again. Yes. In this case, the problem was that the developers of the technology, they really thought through the technological aspect. So I think from a hygiene point of view, this was a very good system. However, when the consumers watched it, they were really appalled by the fact that the animals were in a box for all their life. They were just in contact with the farmer on special moments and not seeing any humans. And whether that's a bad thing or not, I'm not sure. But at least for the people who were watching this video, they were really appalled. And the system in the end wasn't taken into production. So the key message here is that make sure to understand who your stakeholders are, who can make or break your design, and use them also in the design process. So the development of technology itself is, of course, you can do that by yourself, but once it's introduced, also be aware that there are others who might have an opinion about it. Oh. And then I have another video to challenge you a little bit more, and that's my final, the final thing I want to show you. So, let me see. Share screen. Share. It's the final thing I would like to show you. And it's a video, actually, I hope you can see it, of sleeping cows. So this video was made by Jeffrey Bewley. He's a researcher from the US, and he works on compost-bedded pack barns. And what he saw was that if the cows are in compost, they sleep much deeper, and they really lie down and they really relax. You can see here also the rapid eye movements. And why I'm showing you this video is because normally in compost-bedded pack barns, there is a lot of bacteria. And the risks of a cow getting a mastitis are much higher because she's in contact with way more bacteria. And what they saw was when they placed the cows on the compost-bedded pack barns, there were less cases of mastitis than there were in a regular system with cubicles. And they didn't understand. So then they saw the behavior of the cows, and they saw that they were sleeping much deeper. And then they did an experiment where they checked the brain waves of the cow during the sleeping, and they saw that the sleeping patterns were much better for those cows than the cows that were in the cubicles. And they could actually identify that the immune system of these cows that were sleeping much better was boosted by the sleep. And we know that this is true because that's also true for human beings. So in the end, my message is that sometimes if you can actually understand the behavior of the animals and how an animal works, we don't even have to make a change anymore to the system. We can already improve the life of a cow just by improving her surroundings. So that's my final slide. I have one more slide to show you because I have a lot of colleagues who helped me with this presentation. Oh. So I really want to thank the organizers, of course, but also my colleagues who helped me build this presentation. I hope you enjoyed it. And if you have any questions, feel free to contact me now or later. Thank you.
Alright, 큰 박수 부탁드립니다. Thank you for your very interesting seminar, Professor Duck. We're gonna ask 2 or 3 questions now from the audience. 질문 있으시면.
Well, are there any questions from
At the first, I would like to. Can you see your face video, Professor Duck? All right. Yes. All right.
Yes.
Okay. At the first, I would like to ask. I'm just wondering, when you measure or when you estimate of the BCS from the
Yes.
cow, have you tried to compare or correlation analysis with finer phenotypes such as carcass weight or some production rate as well?
For this study, we haven't done that, so I don't have any numbers about that.
Because it would be very useful when you measure the precisely BCS, and then if we can estimate of the final some production rate to use up that score, I think it would be very helpful to the farm as well. So I'm just
I
wondering.
agree with you. So that's a
Yes.
very good suggestion. Thank you.
All right, all right. Any other question? Yeah. 마이크 이용. 네. 정부의 보조금. So when you're doing that research subject for a smart farm, so did you get any support from the government fund or some other kinds of research fund from the government?
Most of this research was actually being funded by the companies who developed the technology, but it is definitely possible to also get a funding from the government. In our case, it's a bit different, I think, than in South Korea, because we have funding available from the government that is being granted to people who have the best ideas. So it's very competitive. We need to write a research proposal and then compete with other researchers for the money. But it's definitely true that we can get a subsidy from the government if we apply for this funding with a very good proposal.
Can you tell us about the size of that fund for each of the research subject?
I'm not sure really. I don't know the exact numbers, but the research funds can be very different. So, for example, I have one PhD student that is supported by the government, and then that project is 300,000 euros. But we also have one really big project about sustainable farming systems running now, and that is 70 million euros.
All right.
So it can be it depends on the call, how much funding is available.
Okay. So when you apply these kind of some smart farm system in the farm area, so can you ask or can you get some support from the government?
You mean for testing and implementing these systems in the farm? That's not common. So normally what happens is that the development and the testing, like the scientific development is sometimes supported by a government, but as soon as it becomes more commercial, then the companies are the ones who develop it further and then implement it in practice. However, as I explained to you, we have a big issue with nitrogen at the moment. And currently, if you are developing new nitrogen diminishing technology, you can get a fund from the government to test it in practice, because it's also a benefit for the government if we find novel technologies to do this fast.
On the other hand, by when the farmers want to apply that technologies, farmers can get that support from the government or company.
So it's a bit the same there. If the technology is really adding to a problem that we are currently having in the Netherlands, like for example the excess of nitrogen, then there are subsidies available from the government for farmers to support them, but these are minimal. So normally, if there is a technology available, the farmers need to invest themselves. So the return on investment is very important.
Right. Okay, due to the time limitation, we cannot get any more questions. Thank you so much for your seminar and answers, Professor
Thank you
Dark.
for having me.
All right,
It was
thank
a pleasure.
you. Thank you. See ya.
Bye.
All right, bye. 네, 첫 번째 발표는 다들 들으셨지만 정밀 축산 사양 기술 개발 정도로 좀 요약해서 말할게요.
So I think that the keyword would be precision farming. Let us proceed to second speaker, Chris Howarth from Austria Smastex, and he is the CSO, Chief Sales Officer of Smastech. He is going to present on Smastech, and as far as I understand, Smastech is not only working in the Austrian market, but also in other countries, including Germany. Let us invite him.
Good afternoon. Can you hear clearly? Can you hear me? Chris? Your video is stopped. All right, all right. Can you say hello? Hello? We cannot hear your voice at this moment. 체크 부탁드릴게요.
Can you hear me okay now?
Say again, please.
Can you hear me clearly?
Yes, now we can hear you. All right, but
Perfect.
please speak louder.
Okay.
Okay. When you're ready to start your seminar, please start.
Thank you very much. So, firstly, I'd like to say good afternoon, South Korea.
Hang on, please. I think your voice is not clearly here at this stage. So, 오디오 체크 한 번만 더 부탁드릴게요.
Just
Hang on, please. All right. Now we can see only your face video. When you start, please share your slide, okay? Say hello again.
Hello? Can you hear me okay?
I think your mic will be better to closer to your mouth.
Yeah, I've got the pods. Everything's clean coming through. I've done a hearing check, a sound check. Everything looks okay.
All right.
Can you hear me?
Yes. All right. Please start again.
Okay. Thank you very much.
Thank you.
So, good afternoon, South Korea. My name's Chris Howarth. I'm the Chief Sales Officer with Smastech Animal Care. We're an Austrian-based company. in the software and sensor technology space. What I'm going to do is talk you through now, and I'd first like to thank Professor Dirks, because there was a lot of synergies with the previous presentation, and there's a lot of synergies and a lot of information that we can derive from that. But I think one of the most important things, and I'm just making some notes through that, is that there's an absolute critical need that we harmonize and we have transparent methodologies, measurement, monitoring, reporting, and more companies communicate together. The reason for this is some of the points that are maybe not quite clear in certain markets around the world. There's technologies available, and hopefully during the next 30 minutes I will be able to talk you through and introduce the SmaxTech technology to you. But first, we have a very close connection with South Korea. We have a very valued partner in Real Farm Korea Genetics, and we have a very broad customer base existing already using our SmaxTech bolus technology across South Korea. So it's my absolute pleasure to talk to the symposium today and give you more of an insight into SmaxTech and the product, and how our technologies can be used to move towards that carbon neutrality, and various things that are in the pipeline as well coming. So to begin with, first and foremost, our products are centered around the health of the animal. So we know healthy cows guarantee. It's critical that we have that stable and high milk yield. It's critical that we look at addressing the major impact of disease on farm, in particular mastitis and the reduction in mastitis. Where we can do this, we can reduce or show a reduction in antibiotic usage. Across SmaxTech customers worldwide, we report up to 70% antibiotic reduction, which is very significant, because when you look at the ecosystems right the way back to the pharmaceuticals, there has to be a change in mindset. And what I mean by this, and I use the term quite broadly, is that farmers all over the world are very, very resourceful. Now, they're wearing so many hats, running so many aspects and dimensions of their own business, it's very easy to lose sight of what you want to achieve. And what I mean by this is it's about getting ahead of the problem. I use the term firefighting, and in our industry, we generally are faced with a problem, we provide the solution, and then we move on to the next problem. What we do at SmaxTech is we try and get ahead of the problem through the means of early detection. And I'll go through a few slides and explain how and why we do what we do and how it impacts the customer. When we look at insemination index and we look at genetic and genetic profiling, better genetic selection helps aid, and again, looking at more efficient animals. When we look at calving and monitoring carbon detection, it's about ensuring that life is brought into the world via healthy calves, healthy cows, and ultimately, farms, the industry, everyone, it's business, and it has to be sustainable, it has to be profitable, and obviously we have to look at really the environmental impacts right across the spectrum and right across the sector. But also on that, when people have got the ability to have a reduced workload and reduced stress, it allows people to work on the business rather than get consumed working within the business. And this is also a very strong message that we give out to our customers. So what's the path to success? So when we talk about SmaxTech, we are a proven health monitoring system. We believe that everything starts from within. So 24/7 monitoring, early detection, and early detection means getting the problems subclinically before they become clinical, and therefore this helps contribute towards the reduction in antibiotic usage, but also really encourages better farming practices. What we do, and again taking some synergies from Professor Dirks, was that what's data? Companies can provide data, we could provide data in the list format, in reporting, but at the end of the day, what do we do with that data? Here at SmaxTech, we provide recommended actions and we provide signposting towards the problem. So we don't only alert to the issue, but we also tell our end user, our farmer, what that issue is and what the methods to treat that should be. Herd health is very important. We talk about being center and being center of the cow. Of course, early detection means early treatment, means early cure, so the recovery time is much shorter. Because we're focusing on the health of the animal, by default, we get a better reproductive performance and a better feed performance. So all of these things help fine-tune the on-farm efficiencies, which mean significantly reduced wastage, significantly reduced time, energy, money, that all help the system. And when we talk about the system, it's very common, and it's a very common term to use from field to fork or from paddock to plate. We're just one section of this cycle, so this is why it's important to educate and work with companies that are also at each stage of that ecosystem. Of course, carbon detection and monitoring, because life begins, and then we want to manage and we want to prolong life, maximize the performance of the animal, maximize the production of the animal, but also too, we have a pH element where we can really look within the cow, look at rumen pH in order to optimize feed. So when I talk about technologies, and it was a really interesting point, and I'm going to sort of refer back to Professor Dirk's slide about rumen motility. What we have within SmaxTech, because we're bolus and we sit in the reticulum of the cow, we're measuring true rumen, so true rumination. So we're looking at the contractions, we're looking at the duration of the contractions, but also we're differentiating between what is a tick, what is a tremor, what could be feed turnover, also digestive issues, and think about the rumen of the animal as being, let's say, the engine. That's the engine room, just like we have engines in vehicles. When that engine is not performing, the vehicle's not performing. So this engine room is critically important to SmaxTech and what we do and how we monitor. When we then look at a second new development in terms of TrueD, this is True Data, and this is our cloud-based AI and machine learning platform. And what we do here, we have the ability to monitor every single cow that has a bolus inside the reticulum worldwide, where we can look and we can differentiate, we can do pattern recognition, we can look at KPI performancing, and we can take, for example, a European farm based on, let's say, similar herd size to South Korea, 40 to 50 to 60 cows. We can compare that to, let's say, our home market in Austria, where we're also looking around about that 40 to 60 cows. But also we can compare right through to what we know as being the mega farms, the thousands of cows in northern Germany or eastern Germany, across into the US, into the UAE countries. And this is something too that I'll talk about in the parameters and what the things we measure we can pick up on. So, only the most accurate systems bring real success. And there's two words I want you to remember from this one slide. One is calculation, and the second one is measurement. Now, I'm in favor of all wearable technologies. I've got nothing against it. Products have been on the market 10, 20 years plus. These products work, but the products that are external wearables, you will always find that there's huge, let's say, algorithms, calculations behind that in order to interpret the movement, the behavior of the animal. Where we differ is because we are located inside the reticulum, we're looking at core measurements. And I'll go through what we measure in the coming slides. But by starting and actual taking the raw measurement, it means we can so much quicker and more accurately determine changes and characteristics and behavioral changes in order to identify the earliest possible onset of any issues within the animal. So, we look at inner body temperature. Now, in my opinion, inner body temperature and the ability to measure inner body temperature is the most critical measurement parameter. With a 0.03 degrees C level of accuracy, we can pick up the very, very finest of changes to the animal. And in simple terms, we can say anything north of an average body temperature is the onset of an infectious disease. Anything south of a normal body temperature is the onset of metabolic issues, and also a very, very key indicator towards calving detection. With accelerometer-based technologies, we're looking at movement and movement activity, and again, being centered in the core and the core of the cow. It's not influenced by external factors, by various head movements, licking, and general pattern behavior that animals show. This is a straightforward comparison between multi-parameter approach of rumination, of body temperature, and activity. And I'll give you a small view of what it looks like later on in the presentation. Of course, with pH, we're looking internally, so from the pH and looking at the pH, the rumen pH, we're looking to maintain that stability. So in various environments and various system changes and ration formulations, we want to be able to see exactly what happens and how it impacts without the need to, let's say, rumen fistulate, to take samples, to take bloods, and again, it increases and improves the performance and gives us a much faster view of what's happening to the cow to make much better informed decisions. So when we look at SmaxTech overall, we say it is the herd manager 24/7. It's looking, because we've got the early detection, and because the theme of the symposium is how we can sort of work towards, or use smart farming to work towards carbon neutrality, it's baby steps. So we want to do our piece by understanding each cow within, and of course relay that information so that systems can be implemented on farm. So things like reduced medication and antibiotics, or hormones, for example, all improve the status of that food and production cycle and the chains. Maintaining performance is key. Where we see losses, and let's be honest, farms all over the world, small farms are disappearing, large farms are getting bigger. So it's economies of scale, improved efficiencies, on-farm performance is absolutely critical. And we have the ability to monitor that completely with every cow. Because of that, we can look, and because of using our TrueD programming, we can improve the KPIs. So we can cluster farms, we can take that data, and that data is processed anonymously. So we use that data, each farmer has their own data and their own access to that data, but we can take that data and we can look at pattern recognitions, and we look at changes, and we can preempt. So things like in a region, in a specific market, let's say South Korea, for example, if there's an increase in pneumonia, then we can look at those farms and we can identify if there's an increase in pneumonia, and we can therefore start to recommend and advise before the problem becomes too severe. Same thing with heat stress, and I just want to touch on this a little bit later. But first, a very simple overview of, let's say, how SmaxTech works. So as a technology, we have the bolus technology. The bolus technology is applied orally, same way that you would put a mineral bolus into an animal, and the bolus sits in the reticulum. The bolus data is then sent to a gateway, and this gateway sends the information directly to the cloud server. The green box next to the gateway is our climate sensor. So the climate sensor goes in the barn. The climate sensor is measuring the ambient temperature. That then cross-references the internal body temperature of the cow, and therefore we can indicate the onset of heat stress before the cow actually goes into stress. Now, excuse me. One of the things here, obviously, if there's no systems for cooling or inadequate ventilation, it's very difficult. And this is about education and educating farmers on what needs to be done in terms of improving on-farm practices. But in the more arid, hotter countries, where we have water systems, sprinkler systems, and fans, we do a lot of work in these hot countries where they're connected to the fans and the water cooling systems so that they can be turned on much sooner, and therefore they're using less electricity and less water. And this is a major, major cost savings in markets. In particular, we have a very, very high level of uptake in Israel, for example. Super hot climate, August in particular, getting up to 50 degrees C. We can see very, very quickly when cows are approaching heat stress, the systems can turn on, they can sprinkle some water, and an example was one farm in particular, they were using water sprinklers together with fans so that they were blowing a mist. When SmaxTech was installed and a climate sensor was also installed, it was then decided that there would be 1 minute of water and then it turned off, followed by 3 minutes of wind, so basically the fans. And because of that, we significantly reduced both the water and the electricity impact on that farm, which is a major, major cost saving. And again, it comes back to products that farmers want to purchase need to show a return on investment, or else it's just a product. It also needs to be followed up, supported and trained. And this is something that has to be done with each customer. And SmaxTech as a company, we also provide more support people than we've got, let's say, dedicated salespeople. So once the data comes through and the data's gone to cloud, it's then processed in TrueD. Then it's formulated an example, the transmission from the cow to the base station to the cloud and back to the app, the smartphone app or a web browser access is around about 0.2 milliseconds. So it's very, very fast processing, very fast measurement and very fast data interpretation. Excuse me. So the advantages of this bolus technology. So when we look at the bolus technology, it's administered only once. And this is something, so once the bolus is inside the cow, from a consumer point of view, it's invisible. So there's no collars, there's no tags, there's no ankle bracelets, leg tags, pedometers. So it's very clean, it's very, very aesthetically pleasing. And it reliably stays in the rumen. So there's no risk of loss, there's no risk of injury. It's the absolute most precise data in terms of precision measurement. And the measurement data here is not influenced by external factors. So we talk about heat stress, we talk about cold stress. I believe cold stress is something that we don't talk enough about, certainly in the winter months, because it's important because, again, cold stress and heat stress, you're using vast amounts of energy in terms of cooling and generating heat, which again isn't efficient in terms of milk production, performance, fetal growth, or even on the beef cattle, the carcass growth or live weight gain. And the parameters here, as I said before, are measured and not calculated. When we talk about the alerting, and again, from one single device, we've got temperature, which we're monitoring the increase and decrease, the activity, so again, obviously activity and increase of activity for heat detection, but also a reduced activity in terms of sick cows or lame cows when it correlates to a multi-parameter approach. We have the carbon detection through body temperature, the reduced rumination through rumen motility measurement. We're looking at insufficient drinking cycles. Now, it's important here, we're not looking at measuring the water intake, it's the intake frequency. And you'll see this from the graphs I'm going to show you shortly. Heat stress is one we've just touched on. And of course, we're looking at reduced feed efficiency. And reduced feed efficiency from rumination and rumen motility, heat stress, water, and also to utilizing the pH bolus. So simply, and again, this is a common message that we hear all the time, you know, we have all of this data, what do we do with it? And if you can't manage, or if you can't measure, you simply can't manage. You're running blind. And I agree with Professor Dirks, the number of customers that adopt technology but don't use that technology is phenomenal. Even on the robot customers, you know, the very, very best users are probably scratching 20 to 30% operational efficiency. The very best. There's so much information there. We now have to work together collectively with companies, whereas we can take that data and we can interpret that data, we can share and merge that data, blend it, and present the customer with very, very good and accurate tools to make informed decisions that can then help improve on-farm efficiency and again, keep taking those baby steps towards the on-farm performance and improving things for the environment. So here, when we look at the measurements, we've got the green band, which is the optimum rumination. We have the green line, which is the actual rumination of the animal. The black line is the normal temperature of the animal, and you'll see the blue line is the live temperature. So every time you see a jag going down, this is when the animal has drunk. So there's water intake. The water has gone into the reticulum, it's gone around the bolus, the temperature of the bolus has dropped, and therefore, obviously, it cools, and then it returns back to its normal body temperature. So from here, we can derive a lot of information around water intake, lameness, water intake frequency. We can look at even practical elements whereby, is the water supply there? Is the water supply broken? Is there no water? Is there enough and sufficient drinking water areas, water troughs in the barns to allow animals immediately after milking, they will go to drink, the creatures of habit. A lot of animals leave the milking parlours, they all go to drink. Is the water temperature too cold? Does the water temperature get recycled in order to reduce that temperature, in order to allow better intake or more intake of water for production purposes? All of these things can be changed and fine-tuned with accurate data. And then, of course, from the activity is looking at the daily patterned activity. We're looking at activity for measuring heat detection, and we'll correlate that with both rumination and body temperature, and also, too, a reduction in activity, whereby cows that are lowing or alert to low activity, we can identify and see what the problem is. When we look at how data is presented, so we try to not overcomplicate things, and I think this is part of this education and feedback from the customer. The dashboard lists, how is the information displayed? You'll see on the right-hand side here, where it's a screenshot on the laptop from the web browser, you've got a very good, let's say, three-tier approach. One's the herdsman, the farmer's action list. What's my go-to? Then we look at the health status, and we're looking at the alert icons. And this is where visually it's important to know and understand when you see the icon, you immediately reference to what the problem is. And then, of course, the fertility status, which is important to look at open cows, fresh cows, pregnant cows, so that you can manage your grouping. When we look at reproduction, and we look at reproduction, precise heat detection, including the recommended insemination time. And one of the notes I took from the previous presentation was talking about the voluntary waiting periods. And this is a really interesting one, and it's one that is up for debate, and it's discussed frequently all over the world. When is the best time? And there's lots of factors, and without sort of drilling too deeply into it, what I look at is I look at the voluntary wait period. When you look at body condition score and animals are losing weight, dependent on the farming type or the system type, it's very rare that you will get cows that hold to pregnant or to insemination when they're still on a downward trajectory in weight loss. And then when the weight gain, or it's about negative energy balance. And this could go into a separate topic. So it's an interesting one. We have customers also that set their voluntary wait period to 70 days. They won't inseminate before 90 days. But the most important thing here, whether they inseminate or not, is that you know when the first true heat following calving begins, because then the system can monitor the cycle and make sure that the animals are cycling correctly and regularly in order to then know at the right time when you can inseminate. What we have here, and I just want to show you, is based on what I call the traffic light system. So you will see here the colours of green, orange and red. Now, when the little black arrow above the colours is that's like the sun timer, that's like the clock ticking down. When the clock ticks down, you're into the window. Now, this will only appear 8 hours following peak heat. So when's the best time to inseminate? So this graph, this chart, this diagram will appear, and it will start counting down to allow you a window of opportunity to look into the future, to see what's practical, whether the cow's in the correct insemination window in the morning when she's milked, midday, or in the evening, dependent on whether it's a 2x or 3x, and when's practical. Of course, there are certain challenges around staff and, let's say, farms that only have the insemination technician arrive once per day, for example. It's very common in Europe that the technician arrives on the farm once. Whatever animals are on the list would be inseminated, but it does allow us to, let's say, it allows us to improve or be able to improve based on our practices. For example, farmers might train themselves to inseminate the animals. They might not use a technician, or they might use a technician and do what we call DIY artificial insemination as well. When we look at this and we look at estrus detection, for example, here on the graph, you can see we have a huge increase in activity, and this is about indexing. It's also very clear to see that there's a drop in rumination, which is a direct correlation. So we have multi-parameter activity increase, rumination decrease, but also if you have a look, we see a small increase in body temperature. So there's actually 3 parameters measuring to allow us the most accurate point in terms of when the animal was inseminated, but also too, during that, let's say, fertilization period, we are seeing certain characteristics that we can then determine what the future is going to be, whether we think that's going to be a successful pregnancy or not. So the idea being increased insemination and conception rates, reduction in the number of days open, and this is significant because each day has a value, and this is quite significant. And it's about shortening the windows, because if you can shorten the number of open days, then it means that over the lifetime of the animal, you will get much more frequent and higher peak milk productions, resulting in higher yield, resulting in healthier cows, resulting in more income for the customer. And also too, when I talk about hormone programs, it's very good when we look at heat detection that it's either less or no need. Now, I wouldn't say never ever, because there's always a percentage of animals that are on estrus, and this can be 15, 20, 25%. So there's going to be some intervention, but it's perfect that, or it's ideal that those cows are identified as early as possible so that they can be treated by the vet. When we look here and I talk about the heat indexing, we then look at developing the technology to give both the window here and now, but look historically back. So this is what I talked about when I mentioned, let's say, correct cycling. Whether this one here, voluntary wait time, 81 days. Insemination was done in the 3rd cycle, okay? So it's not necessarily not getting the opportunity, but the animal needs to be in the best position from a management point of view that she will conceive as early as possible. And things like the number of straws per pregnancy, and I know our partners in South Korea, Korea Genetics, you know, they're very, very good, yeah, in terms of their technical people can interpret the data, they can work with the data, and they get some very, very excellent results on farm. When we look at carbon detection, and again, I know I'm walking through these quite quickly, but carbon detection is critically important. Dependent on the farming type, we saw the manure bedding, the freestall barns, there's cubicles, there's smaller areas, there's overcrowding topics. So all of these on-farm challenges we need to help address in the short term whilst both educating in the long term. So, for example, if we can identify cows that are going to calve 10 to 20 hours before they are due to give birth, we can separate the cows. We can separate them only when necessary. We can efficiently use those calving areas. We can monitor more closer that birthing process. And of course, the reduction in stillbirth rate, mismothering from cows that give birth in groups, cows that are overcrowded that give birth in cubicles. All of these things give the bad message, because it only takes 1 or 2 people to see, as we heard also previously around animal welfare. Our industry is constantly under the spotlight, and we need to not only improve that image globally, but we also need to adopt best practices, and we need to be very proud of what we do. And I think as an industry, we are very, very proud of what we do and what we bring to the market. This is showing you now the majority of the calving alerts sent 10 to 20 hours before calving. This gives that preparation time, but you can also see here, based on the study, it could be 5 hours up to 30 hours. So the point is, you get the alert is tuned, the alert is in line with internal body temperature, and therefore you can act and change management accordingly. When we look at health, and we look at health as being the center point of the SMAC-STEC system, we're looking at detection of feverish diseases, the mastitis, the metritis, so this is where we show the increase in body temperature, as well as metabolic diseases, ketosis, milk fever, irregular water intake, and also heat stress. I'm only going to show you a couple of examples in this because of the time, and then of course I'm happy to answer any questions you've got following the presentation. So here we look at mastitis, and the system, based on early detection, can detect mastitis up to 4 days earlier. Now, if we look at the first chart in the first alert, this is basically what you would get and what you would see. So I've removed all the other parameters just to show the body temperature. Now, when you get an increase in body temperature, what you will see on farm is absolutely nothing. You may not even get any redness, any warmth within the udder to indicate that there's the onset of infection. But this is about training, and this is about support, because then you will see 24 hours later, so a little bit later after that, you will see a second spike. And this is the time that you would probably act, or typically in the beginning, farmers would go in with maybe an udder mint, a cream, maybe a fluid drench, and even an anti-inflammatory. And then the third temperature alert, and bear in mind the icons, so it becomes very visual and easy to see. The third alert is when you are going in and you need to address with antibiotics, because you've got quite a significant increase in internal body temperature, and therefore it's too late. So the message is, once we go through, let's say, an onboarding process and the training process, we want our customers to start acting blind and responding, because let's say if we look at the first temperature increase, and there we went in with the fluid drench, and there we went in with, let's say, a cream, some homeopathic treatment. A, it's a very, very low cost. B, you're looking at getting the inflammation down. And also, too, if you can remove that inflammation as early as possible, the cow's own immune system will also help and find it easier to fight that infection. If it gets to the second marker, and then you go in with anti-inflammatory, there's also a very high chance that you will not get to that clinical state. And where cows are clinical and do need to be treated, then the appropriate treatment, but also the correct culture, what bacteria, is it Staph aureus or Strep uberai, or is it E. coli mastitis? E. coli shows a slightly different pattern, and what we can look at is basically here, a mastitis after calving. So we can see here when we had the calving alert, when it came through, we saw the body temperature drop, we've seen the decrease in rumination, and this is the cycle, and this is what we would say would be quite a poor start, and this cow would be under quite a lot of pressure. And you can see here too, and again, too many alerts can be confusing, too many alerts can be ignored. So what we work on is we work on specifics in terms of alert for specific animals. Individual cows get individual alerts. Any patterned or group behavior drops into a group metric. So let's say, for example, mastitis, we'd look at rumination alert, we'd look at temperature alert, we'd look at feed intake alert. This then would signpost according to the system. You would get an alert to say, this cow has got mastitis, she's in that at-risk period. But as a group, and let's say for heat stress, you would see a full group alert. So when a percentage of the animals hits a threshold, hits a banding, you would then suppress individual alerts and give one big group alert in order to action it. So the system is very smart, and because of the machine learning there, we also request feedback. So if something's not relevant on farm, you can simply say not relevant, and the system will then continue to improve and learn how things work on each individual farm. So when we talk about the future and the future of SMAC-STEC and the bolus technology, because we're doing motility measurements, what we're looking at, or the motility with the number and duration of contractions, And again, this comes a little bit to the next step, and in many research centres where feed intakes can be weighed and controlled, it's easier to interpret the feed intake and even the turnover. But if you think, because we're in the cow and because we're measuring those contractions, it's almost like a contained pump. So if we know what the input is, and if we know what the production rate is, we can then start to determine what potential production is in terms of gases. Also too, with feed efficiencies, we want to look at improving the rumen health, so we know at what point we can get to with the animal and how the animal can maximize the performance without compromising on health. But I think too, when also we look from farm to fork, paddock to plate, when we look at manure quality, I think we underestimate manure, and we look at cows based on the feed types and the TMR, the rations, or even on pasture-based, and we look at the manure composition, and you say, okay, that manure, is it quality manure? Yeah, is it quality manure from a healthy animal, or is it almost like a very watery diarrhea type manure that, you know, it's got high acidity, and, you know, even the urine there having high levels of ammonia. All of these things will impact that manure being processed, being spread onto the fields, being processed, separate the liquids from the solids for the manure bedding. All of these things can be done at each stage of that cycle within that ecosystem. Can we look at changing different feed types to lower methane emissions? These are all future ideas, but because of the bolus being inside the animal and we're able to measure, we're able to see a lot more data and be able to derive a lot more information quicker in order to work with our research partners and find solutions and best practices. So with SmaxTech to success, when we look at it very simply, we want a simple, intuitive interface. We want to be able to offer all functions within one system. We want to provide that stable milk yield. We want to showcase and be very proud of the fact that SmaxTech customers claim, and by feedback, and this is their numbers from our users around the world, up to 70% less antibiotics. Where we can early detect disease and illness, there's less treatment costs. Because we can detect early, there's much shorter and less severe disease progression, which means healthier animals, better for consumer visibility. You know what your cows are doing anywhere because you've got their access. Mastitis, we know it's critical worldwide. No different for you guys in South Korea, but we can detect mastitis up to 4 days before it becomes clinical. Because of that, we can improve the cell counts, we can improve other health. Higher than 90% heat detection rate, and this is taking into account everything. If you took into account just milking animals, you're up at 97, 98%. This looks across through with everything in terms of suckler cows, beef breeding cows, shorter calving intervals. We've got that being formed before calving and far less complications around calving. So what I want to do is just to end there, and I'm happy to take questions, is how's this and how does our product help contribute towards that sort of carbon neutrality? And what we talk about is it's about information and information exchange. And I'm very privileged to be able to speak to you all today at the symposium, because information and knowledge sharing, when we talk about it, we talk about farming practices. We're now going to talk about carbon farming practices. So these are hot topics that are coming. Different farming types, different regions. What are the key issues? We have to talk. We have to talk within the industry, within academic bodies. We have to talk at government level. We have to talk planning level. We have to talk big picture. As I said at the beginning, there's such an important need for harmony and companies needing to work together. I think for so many years, one of the challenges has been companies have had specific products and they've been sort of self-contained, and there's been that competitive market. Farmers are driving change. End users are driving change, and the need to integrate. We have a full open API. We're happy to talk to anybody, any system integration, because for us, even if we were a slave, it's about bringing to the market the product that will give us the most reliable accuracy, in terms of management decisions, early detection, which can only mean good thing for the farmer in terms of profitability, but also too, as it ends up on the plate, the consumer will look at that traceability and want to know they've had happy, healthy, productive animals. So when we look at the demand side of things and when we look at what we can do and what roles we can play, I think, again, a common message is we're all in it together. We all have to stand up and be accountable. Newer business models, you know, we have to look at everything and lobby for change around, you know, income to farmers. We talk about, and it was spoken again about government subsidies, you know, subsidies that aren't just taken and wasted or taken on a technology that's not implemented properly. There needs to be a lot of education. There needs to be, in my opinion, a lot more scrutineering of those funds that go out. New business models, again, we need to identify them, we need to study them, we need to develop them, and also to incentivize, incentivize for further adoption of these carbon farming methods, because ultimately what we're trying to do is we're trying to be innovative, we're trying to bring change, we're trying to product develop, and this takes significant investment. Yes, it does, but it's an investment that is going to better the entire industry long term, because every company that's developing, it keeps everybody honest, it keeps everybody pushing forward. And again, you know, it's a very, very strong topic, and it's one that I've been very pleased to introduce you to today across the SmaxTech product. Again, my name is Chris Howarth. I'm the Chief Sales Officer for SmaxTech, and I'd just like to thank you for your time and happy to answer some questions.
Right. Please close your slide. All right. Thank you. Thank you for your presentation for introduction of SmaxTech. So we're gonna ask one or two questions from the audience. 질문 있으시면 해주시기 바랍니다. 네. 잠시만 마스크가 아니라 아닙니다. 마이크. 예.
Hello, I'm Pang Manwong, a researcher. So actually, I was wondering if this technology can measure the tumor in the rumen, like the capacity. Can the technology measure the capacity of the rumen?
Technologies. So is it changeable, the function of the SmaxTech to measure the estimate of various records depends on the size of the rumen?
No. So basically, the system, once the bolus is active within the animal, it knows basically the same breed types, whether it's Holstein, Jersey, various breed sizes. The system and the way that the technology works, think of it sort of more seismic. So it's looking at the contractions, the ticks, the tremors. So it's not governed by, let's say, the size of the rumen, the size or frame of the animal, or the capacity of the rumen. But what we can do is we can make various changes to increase sensitivity or decrease sensitivity according to the specific farm.
All right. What about the gender or the other kinds of environmental, like a climate or?
No problems at all, because what you find is that within the cow, what the core body temperature is, that's what the other parameters will work and base around. So it doesn't matter what climate you're in. Of course, cows have got, the various, like we do, living in different parts of the world, there's slight changes and modifications in core body temperature. The same thing applies with the cow. So the system gets deployed. Within 8 to 10 days, the system understands the environment that it's in. So then it works based
Okay.
on that environment.
Okay, all right, thank you. And then my question is, can you suggest or recommend what is the under limitation number of the individual animals, cattle in a farm would be suitable to apply the SMAC stat?
Okay, so we work on the basis that in order for the group averages and the group metrics to work, you want to look at a minimum of 20 animals.
20.
20 animals.
Right.
These are 20 animals for, let's say, the true D. However, if you only were interested in using the pH can be deployed in sentinel animals. So 1, 2, or 3, they can be used individually. But
I'm asking that cost-effective number, limitation number. So 20, I can't take care of all of the animals by myself without the SMAC tech technologies. But when I want to cost-effective to apply that technologies, so is it same number, 20?
Yeah, 20. Yeah, 20.
All right. Okay. Thank you. 시간 관계상 우리 질문을 그만 받도록 하고
That's
due to the time limit
all the questions that we can take at the moment.
for your presentation, right?
No problems at all. Thank you very much for having me. I wish you a very, very successful remainder of the symposium. It's been my pleasure. And any questions, I'm happy to answer via email or correspondence. So, yeah, I look forward to hearing from you.
All right. Thank you. 큰 박수
Thank you.
부탁드리겠습니다. 이상으로 두 번째 세션
Brings us
많이
to
늦어졌는데요.
the end of the second session. We're a bit over time. Thank you.